Hello, everybody. Hold on, let me move Nathan to the right spot. There we go. I think we are having mic issues. 1 second. No. Sorry, everybody. Technical difficulties. All right, try now. Still no. Weird. Try again. Somebody All right, chill. This is weird. Let's try something different. All right. One more thing. All right. Now you should theoretically be
Hello?
good.
Can you guys hear me now?
Hey, we're good. All right.
Sweet. Well, last weekend you guys played all CTF mostly. We were thinking about doing rat CTF, but that didn't end up happening. Or at least just it was early in weird format. And Alice was great. So we ended up placing, what was it, 44th on that? But at the very beginning we were up to second place, so sweet. But next weekend Seesaw, so get ready to crush that one. Starts at 4 p.m. on Friday. So what we'll probably do is we'll just start it at 4, those of us who are available, and then take our break for the RE training on Friday, and then spend the rest of the weekend hacking away on Seesaw. So that should be a fun one though. So if you have time, set some aside for that. But to business today, Rowan will be talking about how to make a Linux executable work. I'll let him introduce his presentation, but might run a bit long, so just expect that. It'll be up on YouTube, slide deck, and GitHub repo are available to, links are available in the chat. But I'll let Rowan take it away from here.
Alrighty. I was muted. All right, I'll start again. I'm going to be going super in-depth today on reverse engineering. We're going to be talking about basically all the way from the very bottom to the top, from operating systems to kernels to the programs that run on your computer. And then we're going to talk about assembly. We're going to talk about low-level programming, all that jazz. So, a few general announcements and stuff. I'm not going to assume that anybody knows basically any of what I'm going to be talking about. But I am going to kind of gloss over some general programming concepts. So if you've never programmed at all before, there might be a couple things you're confused about that I will talk about. Hopefully, as I continue, those will get cleared up after I go through some examples. But I'm not going to spend a ton of time on the minutia of each programming language that I'm talking about and stuff. So yeah, the big one, you don't have to know anything ahead of time in order to get something out of this. At least I hope not. Hopefully this is an illuminating presentation for anybody and everybody. I'm going to be answering questions along the way from from Nathan. He's going to give them to me off of Discord, and he's going to be looking at the Twitch chat, and then, yeah. So if you don't already have it, you'll probably want to download our Docker container that's available at our website and in chat. If you don't have that, you probably want it. It has the tools. If you don't want to download that, the repo is available on our GitHub, github.com/boilers. It should probably be the top one. So you can download the source code there instead of getting the Docker if you really want to. And a little bit about me. I started doing CTF as a freshman. I'm a senior now. And I've worked in the defense industry doing similar stuff for a couple of years. So I have a little bit of experience with it, but I'm by no means an expert. Alrighty. Let me just make sure before I get started here that Nathan is hearable on my main slides. You're not, so there's that, and then we also want. Sorry, usually I'm the one managing the stream and somebody else is just talking. I have to do both. All right. Cool. So let's get started. What is reverse engineering? So there's official definitions. You can look it up on Wikipedia. You can do all that stuff. But really, what we want to do is we want to take something that we don't know anything about, and we want to break it apart and figure out as much information as we need to get what we want out of it. So for our objectives for a CTF are going to be a lot different from what our objective would be if we were working in industry, trying to do vulnerability research, if we were working for a company trying to find vulnerabilities in our own software in order to secure it. So the objectives of reverse engineering can change depending on what you're doing, but the actual process is very similar, just a different level of depth. So I've got some examples on here. Probably the most common form of reverse engineering is you get a new job. Your coworker had been fired 2 weeks earlier because he did a crap job of writing their database software. And now you have to figure out what his code does. That's a rough one, but it happens a lot. Another one is I wrote Tickle Me Elmo, but really I prefer the Furby analogy because who doesn't want to rip a Furby to pieces? And figuring out how the circuit boards in there work and all of that kind of stuff. So anything that involves you taking a black box, essentially something you don't know anything about, but that you know does something, and figuring out how it does what it does is going to file under reverse engineering. But the one that we care about today is taking a compiled program that was written in C, or on Friday we'll talk about programs written in C++ and Go. A compiled binary, specifically today we're going to be talking about the ELF format on a 64-bit computer, just to narrow the scope a little bit so we don't get too crazy and overwhelming, and figuring out how it works and getting a flag out of it, because this is a CTF bootcamp, not an industry vulnerability research bootcamp. So first thing we got to understand, whoa, I skipped a demo. So I'm actually going to start off doing a challenge. This challenge is on the Docker, and I'll show how to get it. So if we open up the terminal, right? Terminal button's down here. If you don't already have it, you can just click that and you'll get a terminal. So if we open this up, all we got to do is git clone https github.com/boilers/bootcamp-2020-rev. This has only today's stuff in it right now, because I'm not done with Friday's stuff, but it will have that in it by the time the Friday training rolls around. So if you go into this directory, and then into the day one, you'll see we have all 7 of the demos that we're going to be going through, and then the slides are also available here. That's just a PDF, and it's going to be the same thing I'm going through on my screen. So that is that. And I'm going to start off with the challenge demo. So I'm going to go real quickly through this. Basically, the idea is just to give you kind of a insight into what a CTF challenge in reverse engineering might look like, and a process that somebody might take to solve it. I don't expect anybody to completely understand what I'm doing. The idea is that by the end of the 2 trainings, you will be able to solve this in the same way that I'm solving it, essentially, and understand the same amount of stuff about it that I do. All right, so we're in here. We've got a bunch of stuff, but really the one that we care about is the program. So if we do file star, right, we're going to get the file type of everything in here, and we see there's 2 elf files because I neglected to delete this one. But I'm just going to recompile it. So if I just run make in this directory, it's going to compile the program, and that's the challenge. So first thing I'm going to do is open it up in GDB. And I want to get some disassembly so that I can tell what I want to do, like what this program's doing. So I'm going to disassemble main. All right, so we seed random, allocate 16 bytes of space, we read 16 bytes of input, and then we call a check function. So if we look at what the check function is, we see, all right, so we've got 20 bytes of space, we have loop counter, we're looping down here, incrementing by 1, so probably we're going through our input and checking it against something. And then we're doing a compare against this flag variable. All right, so in 2 minutes, I basically figured out what this program's doing. Chances are, if I had gone in blind and this wasn't a program that I myself wrote, it would have taken a lot longer. But that's essentially all I need to know in order to reverse engineer this program. But if we just go ahead and run it, we can see it's just waiting for some input. So if we just do flag, it's going to tell me I'm stupid a bunch of times and then it's going to fail. But so we know it's iterating through whatever we input. So if we write a GDB script that will basically brute force this program, so I don't need to go through and figure out what it's checking against, although that would also be a valid way of solving this. I can just write a GDB script to solve it for me. Oh, I made a mistake. So I'll just go into what this script is doing while I'm in here very briefly. So basically what we're doing is we're iterating through a bunch of guesses, and we're appending that to a flag, and once we get a character right, we move on to guessing the next one. Very simple, we're just brute forcing through this checker. We also need one more thing before we do this solve. Open program, disassemble the check function. We need a location to break at. So I just copied that. Hopefully it'll let me paste into here, and yes, it will. So we're looking for that address. Each time we get to that address, we know we iterated another time. So now we can source it. And you can see right here, we're brute forcing our flag. It's going to be a little difficult to look at because it's going super fast. But if we just give it a second, we get a flag, welcome to RE. So if I put that flag in, flag, welcome to RE, it says I'm stupid even more times because it's telling me one thing for every character that I get right. And then it says win at the end. So we've won. If this was a CTF challenge, we would have gotten the flag and we would have gotten our points. So let's go back to the beginning. How do we get everything that I just did? So I took that program apart, right? I figured out how it worked, and then I figured out a solution to get what I wanted out of it. But we need to start with way more basic than that. So we're going to start with what is actually in a computer. So as I said before, just as a bit of ground rules for this entire presentation, I'm only going to be talking about 64-bit x86 machines. So x86 is the instruction set. It's what probably everybody watching this is watching it on. unless you're watching my video on a Raspberry Pi, in which case, good for you. But most machines,
A lot of phones use ARM.
a lot of phones use ARM. That's true. If you're watching on a phone, probably not x86, unless you have a giant battery. So probably you're on x86, which is why I chose that platform for this. Also, our Docker runs on x86, so it just makes a lot of sense to do that. And final, it's the most common that you'll see in CTF challenges. Capture the flag tends to be pretty holistic. You'll see ARM pretty often. You'll see some like embedded code on a reasonably regular basis, but for the most part, it's going to be Linux executables on x86 just because everybody has access to it, and it's a good architecture usually. All right. So the critical things that are in your computer. The first one is memory. So this isn't your hard disk. This isn't your hard drive. This is the RAM that's in your computer, right? So you probably got a couple sticks in your motherboard or soldered to your laptop if you have a MacBook. This is where the majority of the data that's on your computer at any given time is going to be located. So it's going to be in memory. Memory is basically just a bunch of cells that store ones or zeros. Nowadays, they can be a little bit different. They can store like a value 1 through 8. But basically, we're going to abstract it to a bunch of cells that store bits or bytes, right? And we can address memory. So if you go to the 0th spot in memory, you're looking at, memory address 0. And that might have one program, and then something else will have another program. We also have cache. So this is similar to RAM, it just runs a lot faster and is much smaller. Cache is actually on your CPU, which is one of the reasons it runs faster, is it's physically closer. When you're operating at 4 gigahertz or whatever CPUs run at nowadays, it actually matters how close physically you are to the CPU. And you can just think of cache as faster RAM for the purposes of reverse engineering in most cases, unless you're doing some serious operating system stuff. Then we have registers. So registers are super critical to know, but luckily there's not a lot of them. So basically what a register is it's a very small piece of super fast ephemeral memory, right? So if you turn your computer off, you're going to lose everything in your registers. Your cache is going to be cleared and your RAM is going to be empty, right? All of those things don't persist through reboots like your hard drive does. But so basically, on x86, registers are 64 bits of whatever information you put in them. Typically, that's going to be an address or an integer, or it's going to be a Boolean value, something like that. So we have general purpose registers. The most used ones are RAX, RBX, RCX, RDX. You're seeing a pattern here, ABCD. Then there's also RSI, which is referred to as the source index, you might hear. RDI, you might hear as the destination index. And then there's some numbered ones, because when they switched from 32-bit x86 to 64-bit x86, they wanted to add some registers, but they didn't just want to keep using letters for some reason. It would have kind of made sense to do so, but it would be weird to use RHX. So I'm sure there's an actual reason for why they're numbered instead of lettered, but we're not going to worry about it now. We also have 3 special registers. Those are the base pointer, the stack pointer, and the instruction pointer. So we're going to talk about the base pointer and stack pointer later and exactly why those are important and what they do. But the instruction pointer is reasonably easy to understand. So imagine you're stepping through a program one line of code at a time. The instruction pointer will always point to the next line of code that we're going to execute. Now in the CPU's case, that next line of code is actually a machine instruction, not a high-level instruction in C or Java or Python, but the idea is basically the same. Then we also have segment registers. Unless you're doing operating systems, once again, you don't really need to worry about these, but just know that they exist and they can be used for some stuff. And we're going to talk about virtual memory a little bit later, and I'll mention the segment registers again, but they're not really used in modern computing too much, at least in context that we need to worry about for our purposes. Then there's also a flags register. that was called E flags on x86 32-bit. It is now called R flags, but you'll see E flags just as much because the actual contents of it hasn't really changed. Basically, all of the 32 bits they added onto it when they went from E to R aren't actually used right now. And that flag consists of the carry flag, parity flag, adjust flag, zero flag, sign flag, and trap flag. We'll talk about a couple of those along the way with respect to some instructions that use and modify them. But the ones that I don't mention, don't worry about too much again. And then there's 8 floating point registers. These are 128 bits wide instead of 64 bits. So they can hold more data, which is good for floating point because we have not only an integer component, but also a decimal. So just think of it as they can hold the same amount of data before the decimal places after. There's different formats for floating point registers, and I'm not going to actually go into depth on those because it's a whole nother animal. But just know that they exist. They're called XMM 0 to 7, and they hold twice as much data as one of the normal general purpose registers. And then we're going to abstract away pretty much everything else. So we also have devices, we have your monitor, we have input-output stuff, we have network. All of that is important, definitely, but I'm not going to go into detail on how it works in the context of reverse engineering because that's a little out of scope of a beginner boot camp. All right, so all of what I said can basically be summed up in the diagram of a theoretical von Neumann computer. This is in contrast to the Harvard architecture, which you can look up. But basically, you have an input device, you have a CPU that has memory and does arithmetic, and then you have an output device. So just think of it as you have a keyboard, you type on it, like the typing cat in that one GIF. Your data goes through the CPU, and then it goes to an output device. And then I'm also going to be using a couple of different data representations. So just for everybody's awareness, if something looks like a normal number, it probably is. For example, 1000 is just going to mean 1000. That's decimal. If I say decimal something, that's what that means. I'll also probably more often be using hexadecimal. So decimal is base 10, right? You count from 1 to 10. That's your normal numbering scheme. The characters that you use to represent them are 0 through 9. Hexadecimal is the same, except you count from 1 to 16 per character place. It just allows you to express data in a more programmer-friendly way, and you'll probably see a little bit of why, because literally everything is a multiple of 8. And then binary, I'm probably not going to say anything in this format today, but if I do, I will write it as 0b. So just know that binary is 0b, hex is 0x, and decimal is what you're used to. So I just talked about a few things. Basically, all you really need to know is computers do stuff. They either consume, produce, modify, store, or show data to you. Everything is just bits and bytes flying around your computer being changed and presented in different ways. Computers don't do anything other than that. They just operate on data. They do exactly what they're told. You'll hear a lot of old people go, "My computer won't let me do X," and that is 100% of the time a lie, because your computer can only do what you tell it to. So if you got nothing else from the last 7 slides, grab that. All right, so we're going to jump into looking at some different languages. The main things you need to know about programming languages are there's a couple of primary types, right? So we have compiled languages like C, C++, Rust, Haskell, Java, Go, Fortran. I think Fortran's compiled. Maybe I shouldn't say that because I'm not sure. But so the main advantages of compiled programs are A, they're very fast, and B, they're very redistributable, right? So if you compile a program on your machine and you want somebody to, or a better example is if you compile a library on your machine and you want somebody to be able to link it, that's very easy with a compiled language, right? Interpreted languages, it can get a little hairier. That's why we have stuff like pip and we have stuff like Lua rocks for installing packages, because distributing stuff is a little bit more complicated than just here's this file or compile this and then use it. Compiled languages are also very fast, right? Because they are converted directly into machine instructions. They run just at the speed of the CPU. There's no overhead on translating instructions in that high-level language into machine instructions because they already are translated. And we're going to talk about compilers here in a minute. Then we have interpreted languages. That's your Rubies, your Luas, your Pythons, especially Python. We love that. In reverse engineering, it's very useful for a lot of stuff. I wrote my GDB script that I just showed in Python. So they both have their place, interpreted and compiled. They're useful for different things. But we like compiled languages because they're super vulnerable, which you'll see when we get to binary exploitation. But you shouldn't fall into the trap of thinking that interpreted languages are inherently secure, because that's not true. All right, so we're going to jump over to the Docker, and we're going to look at some language types, right? Okay, so here's the program that I just showed on the slide in C. So we have a main. We print the output of foo called with the argument of 10. And yes, artifacts, this will be recorded. It will be on YouTube after we're done. So we call foo with 10, which returns bar of n, which in this case is 10 times 2, and bar returns n plus 20 times 2. So if we compile this, and you can just type make because I've already done that for you. I'm actually going to remove the program and then make so you can see the command. So we use what's called GCC, that's the GNU compiler collection. And I'll talk in a minute about why it's a collection and not just the GNU compiler. We output program from the source file program.c with no pi. You don't need to worry about what that means for now. It just makes it a little easier for debugging. And then we're compiling with debugging symbols and 0 optimization. That's O as in owl, 0 as in 0. So if we run this program, it prints out 60, right? So what about in Python? So we have exactly the same program, just slightly different syntax. And we can see that, again, it prints out 60. So functionality-wise, this little example between compiled and interpreted is exactly the same. Then we also have some Java code. And right here, you know you should never be writing Java because there's like twice as many characters in this file as there was in the C file. But Java has its place too. So if we do java c demo01.java, then we can do java demo of 1, and again, we get 60. So the reason I included Java in this demo is Java is what's called a bytecode compiled language. So it doesn't compile directly to machine code like C does. C compiles straight to x86 64-bit machine code, and it runs straight on the CPU. Java runs on a virtual machine that interprets Java bytecode, which is what you actually compile to when you do Java C. So if we do xxd demo01.class, right? So this is our compiled Java program, and there are instructions in here, right? But there's also some other stuff that's used by the JVM in order to A, produce a smaller file, B, run pretty close to machine native speed, although not quite, and C, it will actually interpret some of these as its own type of instructions. And there's an advantage to that too. It's portability. So any machine that the JVM is ported to can run Java code, right? You've all seen the Java runs on 3 billion devices meme. So I figured I would throw it in here. All right. So we've looked at the two, but really three main types of programs, and that's compiled, interpreted, and then bytecode compiled languages. And now let's talk about specifically compiled languages. So what's the advantage to a reverse engineer if you're doing Python code, right? You're going to open it up and you're going to immediately be able to read what's in the program. Now, you can obfuscate Python a little bit. You can make all of your variables one character. You can use metaprogramming to make it really complicated. But in general, you're going to be able to read what that code is. And sorry, I'm going to be grabbing drinks of coffee because A, it tastes good and I have a lot of it, and B, I'm saying so many words right now. So compiled programs are a little bit different. If I open up, so XXD is a command line program. If you haven't used it before, it just dumps out a file in hex on one side, and then it dumps it in ASCII if the ASCII is available on the other side. So if we dump out our program in XXD, we can see some strings, but way more random hex stuff, right? And we're going to talk about what the format of this file is in a little bit. But it's a lot harder to read, I'll tell you that. So Python, you can just open it up and read it. Java, you can decompile it because there's a one-to-one representation of actual high-level Java code and JVM code, more or less. So if you decompile a Java program, you can basically understand what's happening. Compiled programming languages like C and C++ and Rust, it's a bit of a different animal. You get just straight up machine code assembly, and it's pretty difficult to read. And of course, that's what we're going to be talking about the rest of the time. So just know that everything I'm talking about is going to pretty much translate to other platforms. It's going to translate to other languages. Compiled languages, obviously. Reverse engineering Python is just a matter of understanding what weird tricks the developer did. All right, so we're going to go through the steps of compilation now. So there's 4 steps, and this is why it's called GNU Compiler Collection and not the GNU Compiler. So we do pre-processing. This is we run through our source code file and we replace any macros, we replace any type definitions with what's dropped in at the top. So if you do #define x10 at the top of your file, it's going to go through the file and it's just going to replace every instance of that x variable with 10. Then we compile. So this is taking our high-level language C, and this is translating it into a low-level language or assembly, but still in a human-readable format, still in a textual format. After that, we assemble our file. This is taking that human-readable assembly and doing a one-to-one translation of this to the actual bytes that reside on disk, and that's our machine code. And like I said before, that's why C is so fast, is that it compiles down to straight up just instructions that run on your CPU. And then the final step is we link our executable. And I'll talk about linking a little bit later. We're not going to worry too much about that right at this moment. And before I dive into the second demo, well, third demo really, but we index by 0 in CTF, just know that we're only considering the ELF format here. There's 2 other main formats, that's Mach-O and portable executable. Mach-O is for OS X and Mac OS, and portable executable is Windows. If you have a really old Windows machine, like you're running Windows 98, you'll have DOS executables, but we don't see too many of those nowadays. All right. Hopping into this. All right, so if we go to our second demo, we'll see we've got a program.c and we have a program.h. So before we do anything, I'm just going to walk through those really quickly. Okay, so our program.c includes program.h. It rotates the bits in a byte by a certain amount, and you'll see we're using this rotbr, and this is actually a macro that's in the header file we're going to look at in a second, but we're just rotating char star by an amount, and that's it. We also have get name, which just reads in your name from standard in, and we have a main which calls get name and then feeds that into rot, and then it prints out your rotated name. So let's go ahead and look at our header file. All right, so we have our macro, rot_br. So that's rotating a byte by an amount, right? So we're rotating, and if you don't know what a byte is 8 bits. So for example, 0b00000000. So this would be 1 byte, right? And we have up to 256 possibilities here, because either of these can be either a 1 or a 0. So this is what's referred to as binary. So just a quick little binary counting exercise. We start from the rightmost end, and if as we flip bits, we increase by a power of 2, right? Starting from 0. So 2 to the 0 is 1. And then if we flip this back to 0, 2 to the 1 is 2. 2 to the 3 is 8. Yeah. And then you just add all of the positions to the power 2 to the power of the position of every bit that's flipped to 1, right? So if we do 1, 1, 1, we have 2 to the 0, 1, plus 2 to the 1, 2, plus 2 to the 2, 4. So that's 7. I was mistaken before. It's not 8. That would have been this, which would be 15. All right. So anyway, we have this macro rot_br, and this is going to be replaced in our preprocess step, as will this name prompt. And we're going to look at that. And then we have just forward declarations of our functions. Okay, so our first step is that we want to do gcc-e, and please follow along with this. I promise it'll help you understand what I'm talking about better if you follow along. gcc-e program.c, right? So this is just going to print it to standard out, but if we do a comparison, so I'm gonna make this a little smaller, and then I'm gonna run that again so it's formatted nicer. And then I'm gonna put this, make sure we're fitting on screen there. Okay. Okay, so if we open up program.c, right, this is our original source file. So you'll see immediately this is not the same as our original source file. If we just pipe this into program.i, so first thing, we have a bunch of extra includes that we didn't put in here. So these are includes that are dropped in by GCC, right? So we have libc header start, we have C definitions, we have word size, we have features. So these are all things that are required for our binary to run, but we don't have to manually specify them because GCC already knows we need these things and it drops them in for us. So we also have some type definitions. If you haven't programmed in C, basically you can name types to other types. So there's a platform type called uchar, which is assigned to char, and so on. Again, that's not really anything that we need to know about, but it's good to have in mind that when you compile, the system drops things in for you. So we have a ton of stuff that's dropped in for us, but we're just going to go down to look at exactly what we were looking at. So if we go to the bottom of this file, and you can see right here, 818 lines, that's a lot more than the 38 that were in our source. But so in our original source, we have name prompt here, and then over here we have this actual, it's filled in. So we have the whole value name prompt. So this was replaced in our pre-processing step. Up here in rot, before we had this rot_br macro, now we have the actual rot_br macro dropped into our program. And same with name size. So the preprocess step basically goes through and it replaces all of your compiler macros with their actual values. All right, let's get out of here. Let's do the next one. So let's go ahead and do gcc-s-masm equals intel. So we'll talk about this later, but there's multiple dialects of assembly language. I'm only going to talk about, I'm only going to talk about the Intel one because I find it a lot easier to read and also easier for newcomers to understand. So if you wanted an Intel format, you'll want to append this when you're compiling to, when you're compiling your program. Okay. So that'll create the program.s. All right. And so now this looks a lot different. This doesn't look like nasty C code. This looks like assembly. And it sure is assembly. So this is what it looks like after we compile our program, right? So we have main, which is no longer a function. It's now a label. And we have some function prologue, which we'll talk about later. We allocate some stack space. We call our getName function. So again, we're going to talk about all of this assembly stuff in a bit. You don't need to understand what you're seeing on screen, except to understand that when we compile our program, it turns into assembly code that's human readable, right? So I can read this and pretty much understand what the program's doing, but once I assemble it, I will not be able to. So that would have created the program.o. And if I try and vim program.o, I can't. There's some strings in it that we recognize, but mostly I can't read this as code. And if you can, probably see a doctor because you're a wizard. So that is the compilation step, but if we try and run program.o, we can't. It's not, just for the sake of argument, I'm going to give this executable permission just in case that's why, right? And we still can't execute it. It says binary exec format error. That's because it hasn't been linked yet, which is the last step. So if we do gcc-o program.c, and we execute it, we don't want a space in there. And it'll tell me my rotated name is this, because if we take a character and we rotate it by a certain amount, chances are it's no longer going to be printable. So yeah, those are the 4 steps of the compiler.
We have
and
a
again,
question from Dungeon
yeah,
Smasher. Do
go for it.
macros make reverse engineering tougher at all?
No, Dungeon Smasher. They actually sometimes make it easier, depending on what the macro is. So whatever the process the macro is taking would be the same whether it's a macro or whether it's a function. So I guess in some respects it can make it easier, some respects it can make it harder. If you figure out what the macro is doing once and you see that process again, you can drop it in everywhere in the program that you see that same pattern. But at the same time, okay, I'm seeing what is a macro in chat, so I'll answer that in a second. But at the same time, it's a little bit more difficult than function calls, because a function call, if you figure it out inside that function, just write a little comment to yourself and say this is what this does, and then it's annotated everywhere. With the macro, you have to manually recognize it. So it's not more difficult to figure out what's happening in a macro, but it is more difficult to figure out that it is a macro all of the places that it happens. So what is a macro? Let's just flip on back over and I'll just describe it for you. Okay, so I'll just make a program macro.c. So a macro is anything that is pound defined, or you'll also occasionally see pragma. So pragmas are macros that are kind of built into the compiler. So those aren't usually something that'll appear too much and be too useful to know for reverse engineering, but you might see it in code. So just know that technically this is also a macro. So a macro can either be, okay, so really it's just something that's dropped in everywhere in a program it appears. So if I define A10 and then I do int main, we need to include. So include is also technically a macro, because this will be replaced with the contents of standard.io.h that we need in order to get the declarations for functions we're going to use. But if we just printf %d a, right? So this define is a macro. It's going to be replaced everywhere in the program it appears. So this a right here is going to be replaced with the value 10. Now that can be a function, it can be a value, it can be a macro that calls another macro. That's a thing that you can do. So if we do this, so a is now defined as b plus 20. So when the compiler goes through, it's going to replace this b with 20, and then it's going to replace this a with 20 plus 10, which is 30. So yes, you do need to type in pound define. If you just do b20, that's not valid C. So that won't work. But yes, so it is sort of like a variable, but it can represent more than a value. It can also be a drop-in function, essentially. And that's what it's used for a lot, like in that example. So I'm not going to save that. I'm going to go back to So if you look at this, this is not just a value, right? It's a function. So it takes 2 arguments and it outputs a value, right? The important thing about macros is they always have to evaluate to a value. They don't necessarily have to be one, but given 2 inputs, they need to output 1 output. All right. And of course, there's hacks to get around that, but that's the general rule. Alrighty, so back to the slides. All right, so we went through the 4 steps of compilation. Those are important to know just for the sake of understanding what a program actually goes through as it's generated into the format you're going to get it when you're reverse engineering. All right, so next thing to talk about, I'm going to drink real quick, is the actual ELF format itself. So as I mentioned before, this is what we actually get when we compile our program. If we do file program, right, we see program. It is an ELF 64-bit LSB, which is least significant bit, and I'll talk about what that means in a minute. Shared object x86-64, and it tells us a bunch of other information about it. So in case you didn't know, the file program is super useful for telling what a file is. File shell.mix, ASCII text, right? So a lot of times it won't know exactly what format it is, but it will know that it is something that we can, the file program will tell you what file type of file is. I see. Why did it not execute when you used gcc-o the first time? So Ishan, the first time I actually did gcc-c, so that creates an object, but it doesn't link it. Okay, so back to explaining a little bit about readelf and the ELF format and what sections are. So the first tool, and that's kind of a lie because we've already looked at the file tool and Vim, that's a tool as well, is readelf. So basically what it does is it takes an ELF file, and remember when we vimmed that ELF file and it was just all garbage characters? So readelf understands that and tells us information about the ELF file. So the key parts, and we're going to look at what each of these look like, of the ELF format are the ELF header. So this is right at the beginning of the file. It starts at the first byte and it's 64 bytes long. And that contains kind of metadata about the file. It tells us what type of executable it is, what version it is, what platform it's compiled on, etc. Then we have things called program headers. These tell us kind of more overarching information about the program. We have section headers, which are used for specific sections in the program that contain different types of data. And then we have the symbol table, which is string symbols that other programs can either use to look up functions in our program. So if you compile a library, the symbol table is really important for looking up where functions are. And then we also have strings and other things like that in the symbol table that describe, so we'll have function names in them. And we'll see in a minute when we start reverse engineering with symbols enabled, what that looks like in a debugger and why symbols are useful. So there's a little bit more to it. There's some other things that can show up in the ELF file, but we're just trying to stick to the basics as much as possible. So we're going to use readelf. So if we go to 03, readelf sections, and then if you do make, the program's already there, so you don't need to make. But the first thing we want to do usually when we get a new tool is readelf -- help, right? This will tell us all of the options that we have when we're using this tool. And I need to make sure my terminal doesn't go off screen, so I'll make sure of that. I see, how do variadic macros look when disassembled? And, oh, we've already got an answer to that. Good job, Nathan. Thank you. Okay, so we have some options here. We have all, which is going to be equivalent to this. But like I said, the parts of the ELF header basically correspond to the options of readelf. And that's because readelf literally is a parser for the ELF format. So we have the file header, we have program headers, we have section headers, and we have symbols, right? Those are what we really care about, but there's some other stuff. There's also dynamic, relocations, notes. Those are all section types that can appear in an ELF file. So first thing we're going to do, we're just going to readelf -h program. So the parts of the ELF header, and I'm actually going to pull this up on the slides, are defined in C code. So if you're a C programmer, you know that structures are super useful for defining user-defined data types. So we have this structure called elf64 header, and this defines the 64-bit header of an ELF file. And in fact, everything in the ELF header is everything in the ELF file, is defined by structs. So I'm not going to go through all of these. I'm just going to go through the readelf output, but it's interesting to note that all of these parts of the ELF file are defined by structures in C. So if we go back to our readelf output, we see magic number, right? So magic numbers, if you don't know, are used to let other programs understand what type of file a particular file is. When we run the file command and do something like file program, it is actually looking at the magic numbers of that ELF file, and it sees 7F454602, and it's like, oh, I know what that sequence means. That means this is an ELF file. So that's what that magic number does. I think it doesn't literally spell out ELF. Maybe it does. No, it doesn't. And then we have a class, so elf64, that's 64-bit ELF. We have what data type it uses. So 2's complement, that's an integer representation that lets us do negative numbers and positive numbers. Little endian. So when I said I would talk about this in a minute, little endian basically just means that when we have a data type that's larger than 1 byte, our most significant byte is last, aka our least significant byte goes first. So that's what LSB means, least significant byte. So if we have something, a number like OX40, 00000000, if we actually look at the order of the bytes on disk or in memory of those, it will actually be 00000040. So you'll notice these bytes are in reverse order from the actual data. So keep that in mind. It's really good, very important to know, especially when you're doing network stuff, binary exploitation. It's going to be doubly important. For reverse engineering, not so much, except just to understand that that is the case when you're looking at strings and when you're looking at numbers in files and things like that. Then we have version 1, current. There's only one version of the ELF spec. So yeah, version 1. It's nice. All ELF files are going to be version 1 for now. Denny 1111, I'm working with 64-bit. If I was working with 43-bit, I'd be really sad because 43-bit is, as far as I know, not a common thing, so it'd probably be pretty hard for me to learn. OS and ABI, we're on Unix. We're actually on Linux, but Linux ELF files are compatible with Unix. And we're using the system v calling convention. So we're going to talk about what calling convention is in a little bit. It's also referred to as application binary interface, but just know it's called system v. And then there's some other stuff here, but we're going to skip down a little bit. So the next important thing, entry point address. This tells us the address that our program actually starts at. So when we start execution of instructions in our program, we're going to start at this address, 400,400. Then we have start of program headers, 64 bytes. Remember when I said the ELF header was 64 bytes long? The program headers start right after that. And then we have start of section headers. This tells us where in the file the section headers go. And then we have the size of this header, again, 64 bytes, size of program headers, etc. So this tells us basically all of the meta information about how to read this ELF file, what type of ELF file it is, etc. All right. So next one we want to look at is program header. So this is, again, defined in a structure, but we can look at it in readelf. And basically what this does is it -L program. Okay, so file type is executable file, right? So this means this isn't a shared library. This is a program you can actually run. There's 9 program headers starting at offset 64. And here's the types of those. So we have the type program header, right? We have interpreter, which literally tells us is this entire program header is just a string telling us where the interpreter we want to use is. And we'll talk about what an interpreter means for C programs in a few minutes. It's not the same as like a Python interpreter or a Ruby interpreter. This is different. This is used for loading those shared libraries. And we're going to talk about A, why that's important, and B, the very specifics of how it works in a little bit. Then we have 2 load program headers. So loadable sections are actually the only thing that gets put into memory, right? So when you run a program on Linux, when we run an ELF program, the whole file from disk isn't copied into memory. Only certain parts of it are copied into memory, and that's the parts that actually contain our code that we want to run. So those are in the load sections, sorry, in the load, under load. Then we have dynamic that holds dynamic information. And for each of these, we can see the offset into the file, the size, what address it's going to be located at, and the size of the memory once it's copied into memory that it's going to take up. So yes, Denny 1111, there are multiple load sections because of permissions. So if you look at this, this is readable and executable. So this is going to be our main program section. This is going to contain most of our code. And then this one is readable and writable. So this is actually going to, I'm not 100% sure looking at this because I haven't disassembled it, but I'm pretty sure this is going to be what's called our global offset table. And we're going to talk about that quite a bit. All right. The next readelf that we want to look at is readelf-s program. And this is going to show us all of our sections. So if we look up here from when we did program sections, we see section to segment mapping. So the important takeaway from this, sections are parts of the ELF file while it's on your disk. Segments are part of your ELF file while it's in memory. So you'll see we have all of these sections, but we only have 8 segments. Okay, so if we, I'm used to reverse scrolling. There we go. So if we look at the sections, right, we have a symbol table. This contains all of the symbols that we're accessing in our program, right? So we have puts, this prints out stuff. We have libc start main, etc. Oh, that's why I didn't use capital S. So little s is symbols, capital S is sections. My mistake. All right, that looks better. There's 34 section headers starting at this offset into the file. So whenever you see starting at offset, literally your file goes from 0 bytes to however big your file is. And offset is start at 0, count that many bytes in, that's where it's at. It's literally just go to this place, that's where it is. So anytime I reference an offset, it's start somewhere, count this many, you found your thing. All right, so again, some of these sections will look similar to some of the program header information that we saw. So we have our interpreter section, again, that just contains what interpreter we want to use. We have, I'm just going to point out some of the important ones. We have .plt, that's our procedure linkage table. We have .text, that's our actual program, right? That's the machine code instructions of our program on disk. We have read-only data. We have BSS, we have .data, we have global offset table. So I'm going to talk about a few of those in depth, but just know that there's a lot of information in an ELF file, and it requires a lot of information to be able to properly run a program on Linux. So if we jump back over here, we can see some of the most important section headers. So this is just this is not an exhaustive list as we just saw. This is a pretty short list, but these are the ones that we really, really want to know. It's perfectly fine, as with everything in reverse engineering, to do a lot of Googling, look things up as you encounter them and you're not sure. Over time, you'll start to build your base knowledge and you'll recognize more things off the bat, but it is completely okay to start reversing and just Google everything you see. The most important thing is knowing kind of the mental process that you need to take to reverse engineer stuff and being familiar with some of the basics, which is what we're trying to do. So .text, as I said, this is your instructions in your program. Remember, as we compile a program, we go from high-level language down to actual machine code, right? So this is the instructions in machine code that are being executed by your program. And you'll notice right here we have permissions. So this r/x means readable and executable. Now, you'll notice it's not writable. It would be pretty bad if whoever is interfacing with your program had permission to just write new instructions into your text section, because then you could very easily hijack the program to do something malicious. So you'll see, oh, and funny tidbit, the text section on some very old systems actually is writable. So if you obtain an arbitrary write, you can just write a function to do something different, and then the next time it's called, it'll just do that thing instead of what it's supposed to do. So it's a very good thing that text sections are now marked non-writable. We also have .data. This contains any initialized data. So if you do, for example, int, and this is at global scope. So if somewhere in your program outside of a function you do int a equals 10, right? And we'll call this g_a because we like to label our globals so we can tell they're globals. So this would be in the data section. Now if we have somebody says messed up screen. I think it's fine.
There you go.
Now if we have constant data, right? So before I had, int ga equals 10, if we had const int ga equals 10, that data is that value ga is never going to change. So it would be placed into the read-only data section because we never need to write it. All we need to do is see what that value is. Data section, non-constant global scope values can change. So we have a writable flag on that. Then we have the BSS section. Don't ask me what BSS stands for. I always forget, and it literally doesn't matter. This contains any data initialized to 0, and it also contains non-initialized data. So if you just do int a and then hit the semicolon at global scope, that's actually going to be in the BSS section. So implicitly, that's going to be initialized to 0 on most systems. That's not always true, but most of the time. So RO data. Oh, somebody says couldn't see the example. Here, I'll just do it again real quick. I think it's just because I was at the. Is it visible now? So if we do int GA equals 10, right? So that would be a global scope non-constant variable. So that would be in the data section. If we add a const to that, now we've told the compiler this value is never going to change, so it doesn't need to be writable. Now this will be in the RO data section. And if we do int GA equals 0 or int GB and then just hit semicolon, right, in C, that's either initialized to 0 or uninitialized, and so that will be in the BSS section because it will implicitly be initialized to 0. Then we have the global offset table. So keep this one in your head. We're going to talk about it a lot in a minute, and it's also extremely important for binary exploitation. But basically, this holds the addresses of dynamic functions that aren't in our program, but that we want to call. Then we have .got.plt, and got stands for global offset table, of course, and PLT stands for procedure linkage table. Got.plt has little stub functions. They're only 3 instructions long, and they either jump to a global offset table address or they trigger the loader to look up a dynamic function. So we're going to talk through that whole process. Don't worry about it at the moment. And there's some references at the end of this if you want to read a completely exhaustive, I think it's about 600 pages read on this subject. All right. So how programs are run. Before we look at dynamic loading and things like that, we need to understand how Linux works with respect to running programs. So I'll let you absorb some of this code. I actually changed this, so we'll just look at the program in our Docker container. All right. So if we go to demo 4, running programs on Linux, and look at the code, you'll see up top we have some includes. Those are just necessary for some of the functions that we're using. And then in main, the first thing we do is we call a function called fork. So on Linux, we have things called system calls. And basically what a system call is it's a function that's provided by the operating system, aka the kernel. You've all heard probably, well, hopefully, Linux kernel. On Windows, it's the NT kernel, and on Mac OS, it's the Darwin kernel. Pretty much every operating system has a kernel, and what a kernel is a collection of library functions, some of which are exposed to us, programmers, as system calls. On Linux, one of those is fork. So what fork does is it takes our process, right? We have process A, and that's what we're running right now, and it creates a duplicate, process B. So process A and B are exactly the same, and that's all it does, is fork just creates a second process exactly the same as the first one. Now, the return value of fork is different in the original and in what's called the child process. So from here on out, I'll call that original process the parent, and I'll call the new process that's created by the fork system call the child. So the PID, process identification, or process ID, is just a number that says, hey, this process is corresponding to this process ID, right? And Linux uses these for a lot of stuff, but one of them is the return value from fork. So in the parent, we receive the process ID of the child as the result of fork. In the child, we receive the value 0. And this is how we actually tell whether we're currently running the program as the parent or as the child. Because obviously, if we create an exact copy of our program, we need some way to differentiate who we currently are. So, excuse me. We do a little switch case here, and then we have a block of code that's accessed by the child process because we return 0 as our PID from fork. And then we have a block of code that's accessed by our parent process because we return the child's process ID from fork. So the next thing we do to run a program on Linux, and this process I'm walking through right now is how every program on Linux, except for the initial program, is run, right? So all processes on Linux have to be spawned by first calling fork, which creates a duplicate of your currently running process, and then running one of the exec families of functions. So exec obviously stands for execute. And what this does is, so fork, we duplicate our process, right? Exec replaces your currently running process with a different process. So right here, excuse me, I have had nosebleeds all day and it's a little rough. So hopefully I don't start dripping blood on camera. So we have arguments, right? So we're going to run the program ls with the arguments lah/bin, and then we have to null terminate our list of arguments. That's just by convention. So what we're going to do is we're going to replace our currently running process. And remember, this is the child process. We're going to replace our currently running process with the ls process, and we're going to give it some arguments. And then in our parent, after we have duplicated ourselves and run our child, we're going to just print something out and exit. All right, so that's a lot. So if we go ahead, go ahead and compile that program and then run it, you'll see we got the output of ls, so obviously we ran ls. And then if we go up to the top first, we get the printout from the parent. Now, which one runs first is completely non-deterministic. That's just a scheduler thing on Linux, so you can't really rely on one of them running before the other. But typically, in this example, usually the parent runs first. Then we say, hello, I'm the child process, my PID is this. And then we exec, right? And we exec and run ls, as you can see right here. So that's how all processes on Linux are run. If there's any questions about that, go ahead and drop them in the chat. So
now would probably be a goodish time to take a break if we wanted to have a short break in the middle of the
that's a good
presentation.
idea. That's a good idea. So
grab some water.
Yeah, we had planned for this. So yeah, go ahead and grab a drink, get comfy. I will be back in like probably 2 minutes to pick back up where we left off with debugging, and we're going to look at GDB, how it works, how to use it, and how we use it for reverse engineering. So, and yes, Abizu, the PID is somewhat random. Usually it's sequential, but it's actually there's no way to predict what PID you're going to get without having a view into the operating system internals. All right, so it's gonna say on the screen we'll be on at 6:30. All right, we back, but I'm gonna give it another minute before I pick up, just in case anybody is getting snacks. If there's any questions so far, please ask. I'm happy to answer them. Somebody a few minutes ago, I guess Nathan didn't ask me this. How does this work with just-in-time compilers or similar? Does the program have to constantly change permissions on pages, or is there a workaround? So typically a just-in-time compiler will actually be its own program, and it will memory map pages with executable permissions, and then it will copy the just-in-time compiled code into that memory map section with executable permission, and then it will execute it with some sort of stub at the end to return back to the just-in-time compiler. Hopefully that answers that. There's a lot of different ways to implement that, though. That's just one example. Oh, that was already answered by Nathan, too. Cool, 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 cool.
We could have been running so many ads during that break. Made so much money.
Oh no, where's our monetization, Nathan? Come on, get on it. You're the president.
Sorry.
Get us money.
Get us money. Probably be easier just to ask some rich company to give us money. Speaking of, if anyone works for any companies that might want to sponsor us, go ahead and CC us on an email.
Or just drop an X in chat if you want to give me money. No, I think probably the easiest way to get money by doing something like this would be to just have some company pay us to do a training at their company. That seems like the big brain move everybody's doing nowadays. But no, we'd rather do it for free online for twitch.tv and YouTube. All right. I'm going to go ahead and pick it back up. You think that's you think we've been paused long enough? I think so. All right. So we're going to look at debugging. What is debugging, you might ask? So if you were here for the training sessions last week for web, you saw Ryan using the JavaScript debugger in Firefox. That's very similar to what we're going to be doing, but we're going to be doing it on a binary instead of in the web. It's the same process. We're trying to do the same thing, but a little bit different implementation. So GDB is a tool, and inside the Docker, we have a extension called Jeff installed in it. Basically, that just gives us prettier printing, some extra functions, and a little bit more sane defaults as far as printing things out. You can use GDB without Jeff, with Jeff, with there's other options called pwn debug and PETA. Those are all options to extend GDB. And GDB can do a lot of stuff. If you just open it up and hit tab, there's like 1,000 commands that it has. But we're just going to talk about some of the most important ones. So run means run a program, right? If you have a breakpoint set, it's going to run until the breakpoint. We're going to talk about breakpoints right here. Continue is similar to run, but run always starts from the beginning of the program. Continue will start where you are. And both of those just mean go until you hit a breakpoint or the program ends. Then we have the break command. This is used to set a breakpoint. And a breakpoint is just telling the debugger, hey, there's this location in code. When we get to here, I want to stop. That's all it is. We're just going to break execution at that point. And we can set a breakpoint anywhere at any address in memory. Then we have two similar but different commands, and it is pretty important actually to know the difference. So step goes forward one line, and if we hit a function call as we hit step, we will go into that function call and continue debugging inside of it. Next does the same thing. It goes forward one line, but instead of stepping into some function calls, we're going to step over them. So for example, if we're going through main and we hit printf, if we hit step, we'll start debugging inside printf. If we hit next, the printf will just happen and we'll continue going on the next line. So these are supposed to default to forward one line of assembly if you don't have source code available to you. But it's a little finicky, so I tend to use the function step I, which means step instruction, instead of just typing step. Same with next. Typically I use next I, and this can actually be shortened, and we'll see how we shorten commands in GDB. Then there's set. So we can set any value in GDB to anything we want. This is one of the most important things about a debugger, is we can test stuff out without it actually being the program's intended functionality. So for example, if we want the RAX register, remember us talking about registers earlier, this is one of our general purpose ones. If we want the RAX register to equal 10, we just do set RAX equals 10. And you'll notice we have a $sign here, and I'll show you why in a little bit, but basically this just helps GDB differentiate that this is a register and not a variable name. Then we have the X command. So X examines, although this isn't a shortened form, it actually is just X. You can't type examine. A location in a particular format, and the formats for that are the same as with printf. So if you do x/c, it'll examine it in the format of character, and that's how that'll print out. If you do x/s, it'll print it out as a string, so it'll print until it hits a null byte, because in C, strings are terminated with a null byte, so that's the last character in a string. If you do x/d, it'll be a decimal. I is print as an instruction. This one's very useful, and we'll see why in a minute. And we can also add numerical specifiers to print more than one. So we have x/48x that'll print 48 hex bytes. If we do x/48xg, it'll print 48 giant hex bytes. So instead of printing 1 byte, it'll print 64 bits, which is 8 bytes. So this will print 48 times 8 bytes in the format of hex. You don't need to memorize all of these. They're all in the manual, and you can kind of, you can get away with just using a couple of them as long as you know how to do it. Then there's print, very similar to examine, and there's disassemble, which is one of the most useful. We'll use that a lot today, not so much on Friday. We're going to be using GDB a lot today until the last example, and then on Friday we'll use Ghidra, as well as at the end of today. So disassemble will print out the human readable versions. So remember, there's a one-to-one equivalence of the human readable assembly instructions and the machine code on disk or in memory. This will print out the human readable version of that machine code so that we don't have to read raw hex and memorize instruction opcodes. All right. So let's just go ahead and take a quick look at GDB. And we're just going to GDB. And I like to add the -q flag. If you don't add the -q flag, you get, let's see, I think all of this doesn't print out if you do -q. So if you do -q, yeah, we just get this. So it's a lot less crap in your terminal if you use -q. Now, let's go ahead and break main. So we're going to set a breakpoint at main, and you'll actually see at 0x7AE. So that's not the virtual address of where we're going to be starting. So I'm actually going to recompile this, and I'm going to add the -no-pi flag to it. This is going to make it a little easier to demonstrate some of the debugging stuff. So if you want to go ahead and also recompile, please feel free to do that. And that's -o program -no-pi program.c. And then we'll just open that back up in GDB. And now if we set a breakpoint at main, you'll see this is actually the address of main as it's going to be represented as we're running the program. And then we can start our program by typing R. So you'll notice right here, I typed b main. So you can shorten any GDB command to the shortest number of characters that don't conflict with another command. So B, there's nothing else that starts with B, it's just break. So if you type B, it's going to set a breakpoint. R is for run, right? So because we have gef installed, we've got some extra output here that you wouldn't have in normal GDB. So I'm just going to go through that first. But before that, notice we have stopped at the first, well, actually, third instruction of main, but we executed main up to the point where GDB was like, oh, I'm in main, and it broke there at that breakpoint. All right, so gef gives us some nice output. First thing it gives us is registers, right? So here's the list of all of the registers on our system and what their values are. And it also says what that points to if it's a pointer. So for example, 400730 is a pointer to libcsu init, and that's another function. This is a pointer to all zeros. So next thing we have is the stack. So we're going to talk about exactly what stack is and how it works. But basically it's just literally a stack of data. And we have a view of the top few values of that and what they point to, and if that's also a pointer, what that pointer points to. And then right here we have code, so it gives us a couple of instructions previous and a couple of instructions afterwards. So literally just Alex, what I did was gdb-q./program, so that will open up GDB. Then I did break main, so that sets a breakpoint at the main function to tell GDB that once we get to main, we want to stop execution. And then I did R for run. So that R just means we're going to start our program, we're going to stop at main, and here we are. We've reached main. I'm pointing at it on my screen. And we are now at the first instruction of main. So hopefully that was better. I went a little fast at the first part there. So anybody feel free to drop in chat if I'm going too quickly and you need me to redo anything or re-explain anything. So we've now set a breakpoint at main. Let's go ahead and set a breakpoint at this address here. So B, and if you're setting a breakpoint at an address instead of a symbol, you need to put a star there. That's just the rules of GDB. So we want to break at that address, and then we can hit C for continue to continue to our next breakpoint. So if we hit C, you'll see that we have now stopped execution at main plus 28. So then we can step, right? So if we want to SI, we can step one instruction, and we are now pointing to this call instruction. So notice that the instruction pointed to in GDB is not the instruction we just executed, it's the instruction we are about to execute. So what we just did was we did XOR EAX EAX. So if we go ahead and NI, we'll step over this call to fork, right? So we are now on this, which is the instruction after fork. So we've stepped over fork. So another nice thing about GDB is if you've already done something, for example, NI, you can just go ahead and press the enter key again, and it will execute the same thing that you did before. Yeah, I have a weird keyboard. It will execute the last command again. So if your last command was NI and you hit enter, it's just going to go ahead and do that once more. And you can use that because a lot of times in GDB, you'll end up doing a lot of steps because you're not sure exactly where you need to stop. But if you hit continue, you wouldn't be able to see what's happening. So you'll end up stepping quite a bit. So if we continue to step, we're going to get to printf. So now let's step into a function. So instead of just using ni, we're going to use si, and this is going to let us step instruction. So remember, step goes into functions, next goes over functions. So if we step, you'll see instead of jumping over the printf call, this time we're going to go into the printf call, right? So that's that. Now if we want to disassemble main, all we have to do is type disass main, and we get the listing of all of the instructions in that function. We can also disass fork, and this one is significantly longer. But let's just go back to that main disassembly. So we just executed, I want to say this printf call. Well, we can find out. If we use the where command, we can see what our current stack of function calls is, right? So we were at main 40071f in main, and we are currently in printf at plt at this address. But if we go ahead and find 71f, we can see that this is our next instruction. So if we don't want to go there, we want to go here, what we can do is we can set our IP equals that, hit enter, and then if we step, you'll see that we are back in main at our call to printf again. So we can set any register to any value. We can set things on the stack as well. That's a bit of a different syntax. I'll leave that up to an exercise for y'all to look up. But GDB is super powerful. You can theoretically do all of your reverse engineering from GDB if you're good enough and diligent enough. It's an insanely powerful tool. All right, and then the last thing, to quit GDB, it's Q, or you can type quit. All right. Great. So now we're going to talk about, okay, so I already kind of did that demo in the last slide. Now we're going to talk about the dynamic loader / interpreter. So remember when I said there are compiled languages and interpreted languages? Compiled languages also have an interpreter, but it's a little bit different from what you probably expect. So if you remember, a couple times I've mentioned shared libraries and loading. So as an example, every time we call printf, right? Printf doesn't exist in our program. We didn't write the code for printf. It would actually be insane if we did. And I don't recommend that you do it either. It's a lot better to let the one dude who wrote printf 20 years ago have his code just be maintained, and we're just going to continue and use the same printf because it definitely works. Now, we don't copy the code for printf into our program either. What we do is we link against a library that contains the code for printf. So when our program, right, our program.c or whatever, calls the function printf, the interpreter will actually go and say, all right, the function printf, I can find that, and it goes to libc, which is the standard library for the C language. So our program is somewhere in memory, right? libc is also somewhere in memory, and it's going to go doot, 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 here's libc. And it knows, based on the symbol table from the elf format that we saw earlier, what address printf is located in that object. And that's called a shared object because multiple programs can all link against libc and they can all use it. So the interpreter is going to say, all right, here's the function, and here's where you should go to run it. So that's basically how it works. That's dynamic shared object function calling in C. That's how it works. Pretty much every program on your computer is doing that right now. I'm using OBS to stream it. I promise you it's making millions of shared library calls. All right. But let's rewind a little bit and let's start from what happens when we call exec, right? Or more accurately, what happens when we call fork. So when we run a new program, first thing, the kernel looks at the elf header, and it says, okay, what interpreter do I use for this? Remember when we saw that .interp section in readelf? That is a string that tells the kernel, I want this interpreter. And the kernel attempts to honor that request, right? So if we want to use some weird interpreter and the kernel has access to it, it's going to go ahead and use the weird one. Typically, it will fall back to using the standard ld.so that we saw printed out in readelf earlier, though. Then it's going to create a process image. So we're going to talk about how this is laid out, and we're also going to kind of gloss over something called virtual memory for now. But basically what it's doing is it's creating a buffer, and a buffer is just some amount of memory. So the kernel says, all right, give me a bunch of memory. And what it does is it will calculate the size that it needs for that. It'll allocate the buffer or area of memory, however you prefer to think about it. And it's going to copy the process segments from the elf file into memory with the right permissions. So remember when we saw the permissions read and execute, readable, writable. So each of the segments of the program will be marked with the permissions that it needs. So this is super important for security. Otherwise, of course, like I said, we'd be able to write to the text section and just change what the program does. So this is a very critical step, is the setting of permissions on the process segments. Now, I've mentioned sections and I've mentioned segments. So just once more, segments exist only in the memory of the program in RAM, and sections exist in the actual elf file on disk. Then what it does is it's going to perform something called address randomization. We're going to ignore how that works, but basically what it does is we're putting our program at a random place, right? So how does this help? This is also a security measure. When attackers are trying to pwn your program, it helps them a lot if they know what address things are located at. Now, if it's at a random address, it's much harder to go to a particular place in a program if you don't know where it is. So we'll talk a little bit more about this later if we have time, but I'm going to gloss over the details. Then we set up the stack, again, something we'll talk about in a little bit, with information the loader needs to start the program. So that's just general environment stuff, and we can basically ignore what that information is, but there's a couple of variables that the loader needs to start the program. And then, the most important part, we're zeroing all of our registers, and we're basically erasing the previous program state. So if we kept registers with the same values when we execute a new program, it would be pretty bad, right? Because A, it's a security issue. If there's stuff held over from the previous program, then we might be able to get data that we wouldn't have otherwise had access to. It's also just a execution issue. We might be relying on data that's initialized to an incorrect value because it was held over. So we're going to set all of our registers to 0. So then, after we've created the process image, copied from disk our executable code into memory, then we're going to call something called start thread. So this says assuming default RTLD lazy. We'll talk about runtime linking in the next slide, but this is the default, is runtime loading lazy method, which means as we call functions, we look them up, instead of looking up every function as we start the program. So the first thing we do is relocate the dynamic linker. So what does relocation mean? That just means we put it somewhere else in memory, right? So once we have the dynamic linker's location in memory, and remember, it might be random, we don't know exactly what it is, we need to tell our original program where the dynamic linker is located so that it can call functions from it. So that's what relocation is we have something at some arbitrary location in memory. We need to tell the program that's currently executing where that is. Then we grab some of the information that we set up on the stack in this step, and we use the loader to set it up. We're just going to ignore the specifics of that for now. We set up environment variables. So for example, if we have exported a equals 2 in our shell, we need to have access to that in our program. And then we get information about about the dynamic sections in our program. Usually there's just one. When we did readelf earlier, we only saw one section labeled .dynamic. But basically what that does is it gets information about what we're going to need to dynamically load and what libraries we're going to need to dynamically load it from. Then we get some random information from the program header table, and this is the important thing, load shared libraries. So when we call printf in our code, we don't have printf in our program at all. And when we put our program into memory, we still don't have printf. What the loader will do is it is going to say, okay, we're calling this function printf. That means we need libc, which is, again, our standard library. So it's going to do the same thing that it did for our program for libc. It's going to copy all of the code in libc into memory so that it's accessible by the CPU when we need to execute it. It's then going to relocate some shared libraries, right? It's going to put them at a random location, and it's going to start the program. Typically, this is from main. Usually, right before main executes, there's a very short function inserted by GCC called _start. And basically, all that does is it calls main with the correct arguments. But for all intents and purposes, we're starting our program from main, right? Just like every other C program does. All right, so that's a lot of word salad. Once again, go ahead and drop in any questions you have in chat. But basically, the steps are kernel gets memory. Kernel puts program into memory. Loader puts libraries that program calls into memory. Then it starts the program. All right, so the second thing the loader is really responsible for after it starts our program running is doing the actual lookups of the functions that we're calling from shared libraries at runtime. So we're going to continue to use printf as our example. So keep in mind, this process only happens, so I'm going to assume we have not called printf yet at all in our code, right? So we just started running our code. We haven't called printf yet. The first time printf is called, we're going to go through all of these steps. So what the loader does is it says what our program does is it says, all right, we have a call to printf. So it doesn't actually know where the code for printf is. It's not in our main program at all. And in fact, if we go back over to our Docker, on the call to printf, you'll see we're jumping to printf at plt. So if you recall from when I was talking about program sections and segments, this is the procedure linkage table. It's just a table of short stub functions. And as you can see, it is very short. This is the whole printf plt stub function. And if we look at the code here, we have jump at some location, we have push 1, and then we have jump to another location. Okay? So if we go back to this process here, when we call printf, we jump to the PLT entry. So that's what we just saw in GDB. That's the procedure linkage table entry. Then the procedure linkage table is going to look up the GOT, that's the global offset table entry for printf. So the global offset table doesn't have any code in it. All it has is it's just a list of addresses. So if we hop back over to GDB, I'll show you what that looks like for printf. And guava lover is the function of the loader explicitly used to move libraries into place. I don't know off the top of my head the name of the function that does that, but yes, that is a loader function. I'm pretty sure. I read a lot of code in the last week, so I could be wrong on that, but I am pretty sure that is a loader function, yes. Okay. What was that?
Library. Does the loader do anything else other than put libraries in place?
Yes. we're about to talk about the other thing the loader does. In fact, we're talking about it right now. Okay, so if we open up GDB with this program that we were just looking at, right? So we're going to go ahead and look at this call to printf again as our example. And again, this is the 04 running programs on Linux demo. So if we disassemble main, right? If you recall, we have this printf call at 40071A. Now, if we disass this, you'll see we have dump of assembler code for function printf at PLT. So if you remember from our slides, the first thing we do when we get to a printf call is we actually call the PLT entry for printf. So when we call printf, we end up right here. So the first instruction, bit odd, is jump to the value at. So if you see brackets in Intel notation, that means we're dereferencing. So that's the same as if we did star location in C code, right? It's a dereference. So location is a pointer, and we are dereferencing it. So we're getting the value pointed to by some piece of code. So we're jumping to the value at RIP plus OX2000 AFA, whatever this is. Anyway, it's this. So if we x/xg, we're going to print it as a 64-bit value, because if we're jumping to something, it's an address, which means we can be pretty sure it's going to be 64 bits. And we see that the address there is the same as the next address in our PLT printf function. So this is actually the global offset table entry for printf. And you'll see this is actually the same address that when we were looking in readelf and we saw the GOT entry in the section headers, this is the same address that was in there. So we're actually jumping right back to our next instruction. And the reason we do that is because only if this has not been initialized by the loader do we jump back here. And then we execute this jump instruction, which is going to jump to the loader and tell it which function we want to look up, right? So, cool. All right, so we've gone to the PLT entry for printf. We then looked up the GOT entry for printf, and it took us right back to the PLT. And since it took us back to the PLT, then and only then will we execute that final instruction of the PLT, which is a jump to the loader fixup. So what the loader fixup is going to do is it's going to, remember, this is what did the relocation of our shared libraries, so it knows where they're at. So it's going to go and say, all right, you want printf? I know where printf is. It's going to find the location of the start of the actual function printf, and it's going to put it in the GOT entry. So it's going to change that value that jumped back to the PLT to point to the actual start of the code of printf. After the loader fixup does that, it's actually going to restart the call to printf at the PLT. So if we go back over here, now we'll have this value initialized. We'll jump to it. It's not going to take us here. It's going to take us to printf. So we're just going to step through that. If we just do the main run, and I'm just going to next until I get down to that spot. All right, so if we go into here and we step, 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 now we're in the loader. So you can see this is RTLD global RO. So I'm actually going to use the fin function, fin. This is a GDB command to run until we're done with the function we're in. And that's going to run until we're back in main. So now, if we disassemble the printf, right, and we look at what's at this address, remember, this is the global offset table entry for printf. x/xg, again, we want a 64-bit value. Now we can see this no longer points to right here. This points to the actual printf code. So if we disass that value, we see, oh, wow, okay, this is actual printf. And you can see it's a lot longer than our initial printf at PLT that we were looking at, because this is not a stub function. This is the actual code of printf. So yeah, that is how it works. So again, to reiterate, we call printf, which doesn't take us to the actual code of printf. It takes us to the procedural linkage table entry for printf. That PLT entry looks up the global offset table, which takes us back to the procedural linkage table the first time we call printf. Then the PLT continues to execute, and it jumps to the loader fixup, which replaces the GOT entry that initially pointed to the procedure linkage table with the actual address of printf. Then it starts over at the PLT call to printf. Now that we have the correct GOT entry in the global offset table, it's going to jump straight to the actual printf code and execute it. So that's how it works on the first call to printf. Now, that value has been permanently modified in the global offset table, so any subsequent calls to printf will go from printf to the procedure linkage table, which will look up the value in the global offset table. And now that we have it initialized, the PLT will jump to that value, right, which contains the address of actual printf. So this loader fix-up thing only happens once. So in this diagram, the stuff in green happens every time we make a call. The stuff in red only happens the first time we make a call, and the stuff in blue only happens, it happens after the loader fix-up on the first time, and on subsequent calls to printf. So hopefully that's clear. It's a super complicated idea to wrap your head around, but hopefully that was a good explanation of it. And let me know if you have any questions. Dungeon Smasher asks, it looks like the fix-up call permanently modifies the code in memory for the life of the program. Yes, that is correct. We'll talk more about the GOT during pwn, but it's very important to understand for reverse engineering and for pwning how binaries actually do shared library calls, since so much of programming is using libraries. All right. If you can understand what I just said, you were in excellent shape, because it took me 2.5 years to understand how that worked at the lowest level. So you guys had the advantage of having a nice slide with this information. To make this slide, I had to go and read Linux and glibc source code. So hopefully I shield you from doing that, at least for a while. So program images. Remember when we said that the kernel allocates some space for the program? So basically what it does is it's going to, okay, so we do need to talk about virtual memory here. So what virtual memory does is the kernel makes every program think it has access to an entire RAM's worth of memory, right? So if you have 16 gigabytes of RAM, the kernel is going to trick every program into thinking it has access to all of it. That's not actually true. What happens is when the program accesses a place in memory, it's actually accessing a place in virtual memory. And then the computer translates that access at that point in virtual memory to a different place on your physical memory. So the addresses may not be the same, but the data is actually stored on your physical memory. That's as far in depth as I'm going to go about virtual memory. Again, in the resources at the end of the slide deck, there's a 700-page read about it. It's an extremely complicated topic. So the kernel creates program images, right? And this is what we're actually dealing with when we're looking at these addresses in GDB, right? So over here, These are addresses in our program image, right? So those are laid out like so. So at the top of our kernel memory is our kernel memory space. This is reserved for the kernel to use. We can't write or read or access this space really from our program. Otherwise, we're going to get probably a segmentation fault. If you've ever written code or tried to run somebody else's code in C, chances are you've seen a segmentation fault before. But basically what that means is you've tried to access something that you're not allowed to. Then we have a random stack offset. So when I talked about randomization, what I was actually referring to was a program defense technique called address space layout randomization, which is related to writing position independent executables. So if you remember, when we looked at our call to printf, and we see another thing that's similar here, we saw a dereference at RIP plus some value. So what that is something called RIP relative, or RIP relative addressing, where instead of accessing something at a hard-coded address, for example, 0x35FA2, we access at RIP plus an address. And what that does is anywhere in our virtual memory space that we put our program, we can access the value, right? So instead of looking at a particular spot, we're looking at an offset from where we are now. And since we know how big our program is and we know where everything in our own program is located, we can compile in such a way that wherever in memory we put our program, we're able to access all of our variables, all of our globals, all of our functions, right? So that is something called position independent compilation or execution. So whatever position we put our program at, we can execute it just the same. That's very related to a second technology, like I was about to start talking about and then realized I needed some background, called address space layout randomization. So this is something that the kernel does when it's creating process images in order to defend against attackers. Like I said, if you don't know where something is, it's a lot harder to attack it. So what it does is it randomizes where our parts of our program are located in memory. And the reason it's able to randomize them is because we've compiled with position-independent execution. Now, earlier, when I compiled my program with that -no-pi flag, I was actually turning that off for my main executable, but it's always going to be on for our shared libraries because they were compiled with it. So, back to our process image, right? So we have a randomized offset here between our kernel memory space and the start of our program stack. So a stack is just a data structure that's implemented at all levels of our computer, right? So our hardware supports the stack, our operating system, very importantly, supports the stack, and our program is written to take advantage of the stack. So what is the stack? Basically, it is just implemented using two registers, right? So we have values, and as we call functions, we put things onto the stack and we move from high addresses to low addresses as we add stuff. So if we put an integer here, a char star here, a character here, we're just putting things on top of the stack. So notice I do say the top, but I'm moving my hand down, and that's because the stack starts at the highest address. So the bottom of the stack is the highest address. Then we have a random memory map offset, right? So again, address space layout randomization. Very important for security, but it does require us to put things in different places. Then we have this memory mapped segment, and this is what actually contains all of the code that is for our shared libraries and any other times that things called the mmap function or something similar to it, that's all going to appear here. So shared libraries will all appear here. And in fact, if we go back to GDB and we do something called info process or proc mappings, we can see exactly where in memory these things are located. So you'll see our program is at the lowest address. Then we have our global offset table and our, well, our PLT and global offset table, one of these is one of them and one is the other, but it doesn't particularly matter. Then we have our heap, and then you'll see in the middle here, we have a bunch of shared objects, right? So those are in the middle between the stack and the heap. So the heap starts at the lowest address here, and it grows upward in memory, so towards higher addresses. The stack starts at the highest address, and it grows downward towards lower addresses. So they grow towards each other with shared libraries in the middle. Makes a lot of sense, I think. Then, like I said, we have the heap. So this stores all user allocated things. So the heap is not changed except by code that the programmer wrote, whether that's library code or your code. So we use the heap to store permanent variables that we want to keep track of throughout the execution of the program. The stack is used for local variables inside functions. Then here at the lowest address, like we just saw, we have BSS, we have data, and we have text. And this is somewhat of an abstraction. We also have the global offset table and the procedure linkage table and some other nice stuff that gets put in here. But pretty much this is, if you took this and you looked at memory like we just did over in our Docker, the memory of your program would more or less look like this, in this order, pretty much every time on Linux. All right. So that is pretty much all the information about programs on Linux and ELF files, about kind of like the meta high-level overview of information. So now we're going to start getting into the nitty-gritty of actual assembly and how programs are written at the assembly level and read at the assembly level, which is really the bread and butter of reverse engineering. But unfortunately, in order to get there, you kind of have to understand how your program works with respect to the operating system before you can read what the program does. Or at least I believe it helps a lot to have a background understanding, because you can read assembly code without understanding how it's running on your machine, but at some point you're going to need to know how it runs on your machine, and that's a pretty big undertaking if you don't have kind of a base level knowledge of it at the beginning. All right. So, drink. Assembly language, like we said, is the human readable one-to-one translation of machine code into characters that we as humans can read. So remember when we compiled with -s, we got something in assembly. We got our program written in assembly. And like any programming language, assembly is a programming language. You can program in assembly if you hate yourself and you're mad, or if you're required to by class, or if you really need to optimize something, or the final one, and my personal favorite, you're writing a CTF challenge. So any of those are good reasons to be writing in assembly, and because of that, it's a language. It has syntax. So like I said before, when we use GDB, I'm going to refer to everything in Intel syntax because I think it is significantly better and more readable than AT&T syntax, but I'm going to mention both here. There's also AT&T syntax. This is actually used by GCC and GAS, which is the GNU assembler, which is part of the GNU compiler collection. Intel syntax is used by NASM and me, Rowan, who's who you're listening to. So we're doing what I want. So here's an example of both. These are the same exact instruction written in Intel and written in assembly, right? So what this instruction does is it moves from the location at, remember we have brackets, so that's a dereference, which is equivalent to the star in front of a pointer. So we're getting the thing at this location, right? That's what the bracket means. So we have some location pointed to by RBX plus OX10, which is 16, and the brackets are getting the value at that location. Somebody asks, can you give an example where you had to write assembly for a CTF challenge? So I wanted to do a CTF challenge where I used some AES shift instructions kind of out of context. So basically, the user gave some input, and I used the AES encrypt function on each character of their input. So it's pretty hard to write C code that convinces the compiler to use a particular machine instruction to do something. And so to do that, instead of calling a function in assembly from C, I was just like, screw it, I'll write the whole program in assembly. And I did that. In fact, I could just pull it up right here. Sorry to go off on a tangent, but this is actually a good thing to consider. All right. So ignore the little "we found potential vulnerabilities in your dependencies." That's just Node being Node. But so this is a program in raw assembly that I wrote to make a CTF challenge, right? So I wrote this challenge, and basically it's pretty readable assembly because it was written by a human, but it is still assembly language, right? So writing assembly happens on both ends of CTF challenges. It happens when I write challenges that I want to be written in assembly, and there's also a lot of challenges where you will get for example, a specification of a custom assembly language that you need to write code in. And the CTF host will just give you a specification for this assembly language, and you'll have to write a program, usually that fits within 100 bytes, and that produces some particular output. So writing assembly is a good skill to have, but it's not. You don't really need to be fluent in assembly. It's perfect because usually you try and write as little of it as possible. It's perfectly fine to just be Googling the whole time, like I was when I wrote that example I just gave on screen. So back to our example of each. Right here, we are moving the value at rbx plus ox10 into the register rax. And then somebody says, can you link your GitHub? You can just look up github.com/boilers to find our boilers GitHub. Thank you, Nathan. And then this right here is AT&T syntax doing exactly the same thing. So we're moving into the value, into the register rax, the value at rbx, and actually this is wrong. This should have a % sign in front of it. My mistake. The value at rbx plus ox10. So you can probably tell this looks a little grosser, and it's also backwards. So in Intel syntax, typically we have source, destination, source. In AT&T, typically we have source, destination. So from here to here, and in Intel we have to here, from here. It's a matter of personal preference, but it's good to be aware of both. All right, so some important instructions in x86 64-bit assembly. First one is push. So this pushes something to the stack. So remember when I said that the stack starts at high addresses and grows down? One of the ways we do that is by pushing a value onto the stack. So that will put something right at the bottom, and then it will decrement RSP, which we'll talk about in a minute, but it points always to the top of the stack, which is at the lowest address. We also have pop, which does exactly the opposite. It pops the value at the top of the stack, or the lowest address, into a particular location. So that can be a memory location, or it can be a register. And then it increments RSP, because we're going back up to higher addresses as we shrink our stack. Then we have move, which in Intel syntax is move to destination from source. And in fact, that's not, the move mnemonic is a bit of a misnomer. It actually copies the value. So if we go back up to here, if we move into RAX from RBX plus OX10, we're not deleting the value from here, we're just copying the value from here into RAX. So just keep in mind it's a copy, not an actual move. So it's more like the cp command on Linux and not mv. Then we have call. So what this does is essentially, to us, it calls a function. But really, in assembly, what it does is it pushes RIP. Remember, RIP always points to the next instruction that's going to be executed. It pushes that to the stack, and then it jumps to a different location, right? So when we call printf at PLT, for example, we push RIP, which points to the next instruction in main, to the stack, and then we set RIP equal to the value of the beginning of that function, so that the next time the CPU cycles, it's going to start executing in printf at PLT, not from the next value in main. Then we have a bunch of arithmetic instructions, right? So we can add arguments, we can subtract arguments, we can multiply things, divide them, XOR them, shift the bits or bytes left or right, etc. So there's a lot of arithmetic instructions that you can do in assembly. So just keep in mind that is a thing. Yes. Then we have a few more. So all of these instructions on this page are control flow, right? So what control flow is in your program when you're writing if statements or while loops or for loops, things like that. Those are all control flow. The switch statement that I wrote in our fork and exec example is control flow. And the way those are implemented is almost always with these three instructions. So the first one is jump. So we already kind of talked about jumping using a call instruction. This doesn't push RIP to the stack. This just goes to another location. So there's some conditional jumps that we can use as well. So jump if the result of a comparison is less than or equal, jump if it's greater than or equal, jump if it's not equal, jump if it's equal. So you kind of see the analog between this and high-level programming, right? So we do if a equals 10. We would compare the value at a to the constant 10, and then we would use the JE instruction to jump somewhere if that equality was satisfied. So just a note about these, if you remember from the very beginning, a while ago, I don't know exactly how long I've been going, but it's been a while. If you compare, or if you remember the flags register, what we typically do is we do a compare instruction. So we compare two values and we set the flags accordingly. So these are the rules we set the flags according to. If they're equal, we set the 0 flag to 1 and we clear the carry flag. If the first arg is less than the second arg, we clear the 0 flag and set the carry flag, etc. So there's different rules for each result of the comparison. Then after we do a comparison, those flags are set, and we can do a jump instruction to look at the value of that comparison and jump accordingly in an if or a for or a while loop. We also have the instruction test, which ands bitwise two operands together, and it checks if the result is 0 or not. And that sets the 0 flag, so that can also precede a jump instruction. All right. Somebody asks, can we use link register in x86 for function call? Thank you. No, so there is no link register in x86. That's actually an ARM thing. All right, so stack and heap. So we've already touched on this a little bit. We've talked about the fact that the stack is at the top of our process image and it grows down. The heap is at the bottom of our process image and it grows up. Now the stack has, all right, so we'll talk about stack frames in the next slide, but basically every time we call a function, we create some space in the stack frame, and anytime we have a local variable inside our function, that's where that goes. It goes on the stack. So if we have local variables, just remember, local goes on the stack. Now, if we call one of the malloc family of functions, like malloc, calloc, realloc, that data is going to go on the heap. And that data doesn't get destroyed by any normal system operation. So we can be confident that unless we deallocate it, it's going to stay exactly where we put it. unless somebody hacks us, and we'll be talking about heap exploits in 2 weeks. But let's talk about stack frames. So all functions, well, not all functions, but most functions have what's called a prologue, and they have what's called an epilogue. And this is related to, but not exactly the same as the calling convention that we'll talk about next slide. So the function prologue is, in x86 specifically, this is going to be a little different on different platforms, is first we push the base pointer. So what the base pointer does is it points to the highest address or lowest location on the stack in our current stack frame. So each function has a stack frame. The base pointer points to the lowest memory in our current function, essentially. So we push the base pointer from the function that we're in. And keep in mind, this is the process that happens when we call a function. So if we're in main and we call foo, foo is going to push onto the top of the stack, the base pointer from main. So essentially it's going to save where it was. Then it's going to move the stack pointer, which keeps track, remember, always of the top of the stack, into the base pointer. So what it's doing is it's making the foo stack frame, it's putting the bottom of it at the top of the stack frame for main. So we have main here, we create foo here. Then we have typically, for local variables, we'll subtract from RSP equal to the total size of all local variables, right? So we want to get space on the stack in order to fit all of our stuff in. I'm holding it too low. So we've got RBP, we've got stack space. And remember, when we execute a call instruction to call a function, we push RIP before we jump. And so actually on the top of the stack, we have our saved return instruction pointer, or saved return pointer, saved instruction pointer, whatever, however you want to refer to it. We save where we were first on the top of the stack. Then at the beginning of the function that we jump to, we push our base pointer onto the top of the stack. Then we set our stack pointer equal to, we set our base pointer equal to the stack pointer, which now points to here. So our stack pointer points to here, then we set our base pointer to here, and then we subtract from our stack pointer equal to the amount of space that we need in our function. So that's the prologue. That's what happens when we call a new function, is the call instruction saves where we want to come back to in code. Then we save where we were in memory. Then we get however much space we need in memory to do the stuff we want in our function. Then we have some program body, right? We don't really care what that is at this point. It could be anything. Let's just assume this is the function printf or our function foo, whatever it is. It'll be about the same. Then at the end of the function, we have an epilogue. So what this does is it's going to take us back to where we were in our previous function. So we execute the leave instruction, which what that does is it's going to move the base pointer into the stack pointer. So what that's going to do is it's going to move our stack pointer back up. So it was pointing to the end of this OX10 space here. Our stack pointer is now going to be pointing to the location of our saved base pointer. The leave instruction then does pop RBP into, pop RSP, which, no. Let me restart. The leave instruction first moves our base pointer into our stack pointer. So that's going to move our stack pointer from here where it was, and the stack pointer is now going to point to this location. Then we're going to pop into our base pointer. So this is a copy of what our base pointer was in main, which called our current function. Now we're putting our base pointer back to where it actually was, right? And remember that base pointer is just a register that contains a location in memory. Same with the stack pointer. So once that's done, our stack is back where it was in main. and then we're going to execute the ret instruction. So our stack pointer, after popping this, will be pointing to our saved instruction pointer. The ret instruction just jumps to our saved instruction pointer. So it's going to start execution at the place where we would have gone next after our function call. So hopefully that's clear. This is a bit of a better description of that. So just say we're executing main, right? So we have two local variables in main, and those are on the stack. Those are int a and int b. So somewhere in the code of main, we call the function foo, right? So our base pointer was pointing, and this arrow is actually incorrect. It should point to here, and this arrow is also incorrect. It should point to here. I forgot to edit that. But just remember the saved base pointer is the same location of the base pointer. So we called foo somewhere in the code of main. And when we called foo, we push RIP, then we push RBP at the top of the prolog in function foo. Then we allocate some stack space, which we're just assuming contains these two characters, or these two variables. Then somewhere in foo, we call bar, and the same thing happens. So we're going to push RIP with our call instruction. We're going to push RBP with our prolog of bar, and then we're going to update our stack pointer and our base pointer. So our base pointer is now going to point to the base pointer in our current frame, and our stack pointer is going to point to the top of the stack. So when we return from bar, we'll go back to our base pointer pointing here, and our stack pointer pointing here. And then likewise, when we return from foo, our base pointer will point here, and our stack pointer will point back to here. And again, once we pop RIP in our ret instruction, our execution is going to continue where it left off. All right, so calling convention and ABI. So this is application binary interface. This is how functions on your computer talk to each other, right? So if one function expects its argument in RAX, RBX, RCX, and another one expects it in RDI, RSI, RDX, we're going to have a problem. So all functions on your system more or less need to use the same calling convention in order to correctly interface with each other. That's why it's called application binary interface. So it's very clearly defined, and it's not terribly complicated, unlike some of the other stuff. So I'm actually going to well, I'll talk about it and then I'll give a quick example. So arguments to functions are passed in these 6 registers in order. So your first argument is passed in register RDI, second argument passed in register RSI, third argument RDX, fourth RCX, R8, R9, in that order, right? So if you have a function with more than 6 arguments, and don't do this unless it's a variadic function, because you should keep your function calls small and modular. But if you do have more than 6 arguments in a function call, those will be passed on the stack. So they'll just be pushed in order. So your 7th argument will be pushed, then your 8th argument will be pushed, then your 9th argument will be pushed, and then the function that you call will just pop them off the stack into whatever register it wants to use them in. The third definition of the system v ABI, is that when you return a value from a function, it has to be in register RAX. So if we have a function x that returns 10, that function will put the value 10 into register RAX, and it's going to execute a return. Then the program after that, if it wants to access that returned value, it'll just look in the register RAX. And then the last rule is functions must preserve, so this word preserve, RBX, RSP, RBP, and R12 to 15. I see a question, I'll answer it in 1 second. So basically what this means is if there's something in those registers before we call a function, that same thing better be in there after the function is done executing and has returned back. And typically this is just done by saving them onto the stack and then putting them back in the registers once the function is done executing. So dartfrog0502 asks, how does it know how many arguments have been passed onto the stack, if any? So that's actually the programmer's responsibility. And there's some stuff in the standard libraries related to variadic functions that can help you here. But pretty much it's the programmer's responsibility. For example, printf will use format specifiers to know how many arguments are passed on the stack. So it knows each time it encounters percent something, if it has more than 6 arguments, or if it hits, excuse me, so the first argument to printf, I'll just start over with this example. The first argument to printf is a format string, right? So we've got RDI, so that format string is passed in RDI, and I'm actually going to hop over into a terminal and give this as an example. Okay, so if we execute printf, and printf is a variadic function, so it can take as many arguments as we want, is what that means. So if we do %d, 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 2, 3, 4, 5, 6, right? So we have our first argument. We have 1, 2, 3, 4, 5, 6. Okay, so there are 7 arguments to this function, which means that this last one will be passed on the stack. Theoretically, there's some optimizations that printf does that makes it not actually a guarantee, but in our model of this is you programming, this 6 we're going to assume is passed on the stack. That's an excellent comment. Thank you for that. Okay, so the way printf works, and this is why I say it's the programmer's responsibility, is each time it encounters a format string, for example, %d is a format specifier, sorry, it's going to look at the next argument. So the first one, it's going to look at the second argument to the function. The second one, it's going to look at the second argument, and so on. Now, when it gets to the 6th one, it knows that it needs to look at the 7th argument to the function. And so it's going to say, okay, I know by the calling convention that if I'm accessing an argument past the 6th, I need to just pop something off the stack. And so it's going to do that. It's going to have 6 on the stack, it's going to pop it, and it's going to use that. And that's basically the same with any function that uses more than 6 arguments, is the function knows how many arguments it needs to access, and so the compiler will say, okay, we're accessing argument 7. That means in this function, we need to pop, and then we can use it. So hopefully that explains that adequately. So yeah, arguments are passed in this order in these registers. Additional arguments passed on the stack. Return value is in RAX. Those are really the most important things. Don't worry about preserving registers. You're not a compiler author. You don't care. All right, so let's go ahead and reverse engineer something with no source. So before we had a source file in the directory, and we had symbols in our program. So I would say probably 85% of challenge authors in reverse engineering are too mean to give you symbols in your program. So they're going to do something called stripping the binary, and we're going to go ahead and do that right now. Oh, not in my Docker. No, I don't want to save this. Also, hi, Justin. Hope you're doing good. Oh, 06. Okay, so if we look at our make file, basically what we're going to do is we're going to first compile our own shared library. So this is just a very simple shared library. I'll open the code in a minute, but what we're doing is we're compiling an object, and then we are making a -shared for shared library on our, just in our current directory. Then we're compiling a program against that shared library, and notice this -s flag. This is strip. This is the meanest thing a challenge author can do to you, and I try not to do it except to prove a point with one challenge in the bootcamp. So look for that, and come back and reference this video when you do it, because it'll make it a lot easier. All right, so we're compiling a library, we're linking against it, and we are stripping our result binary. So if we do rm program and then make, so you'll see we compile liblib.so, and then we generate this program. So if we just /program, it's going to say error while loading shared libraries. Can't open shared object file, no such file or directory. And the reason for that is our system is not looking in our current directory for shared libraries. It's only looking in our library paths, which are /lib and /usr/lib, right? So there's no reason it would look in our current directory, so we have to tell it to. So if we look at this run.sh file, we do ld library path equals dot. If you haven't used Linux before, dot is our current directory. It's just a relative reference to it. And then /program. So if we go ahead and do that, ld library underscore path, and if you can't see it, those are underscores in between an ld library path. I'll go ahead and make my terminal a little bit smaller. Equals dot/program, right? So this is going to run our program, and it's going to tell the loader. Remember, the loader is the one that goes and looks for libraries. So it's going to tell the loader that when it looks for libraries, it should look in our current directory. All right, so our program runs now. So let's go ahead and look at the code. So this is the code for our shared library. We just have one function, mom get the camera, and it prints out mom get the camera and returns a random number. It's just a stupid little function. And then we have program.c, which declares that there is a function called mom get the camera, but it doesn't actually define it, right? So this is just yet another, I'm trying to ram home, shared libraries are a thing, and you should think about them. And then it calls that function from our shared library. But when we go ahead and run this in GDB with no source code, we're going to have some issues. So let's go ahead and do that. gdb-q/program. So if you remember, when we told our shell where to look for shared libraries, we also need to tell GDB. So a nice thing about GDB is if you put exclamation point at the end of anything, it will execute it in your shell instead of in GDB. So if you realize that you needed to cat out a file while you're in GDB, you can just hit exclamation point cat GDB init. So GDB inits are super handy little thingies. Basically, you can write a file and then you can source the file in GDB, and it will run every line in that GDB script, essentially, as if you were running it on the GDB command line. So this is A, a good way to script GDB, and B, a good way to just very quickly execute your setup commands. And I've got a couple in here. Set disassembly flavor Intel. If you don't have Jeff installed, will make GDB print source in Intel format instead of AT&T format. And some stuff like that. So we're just going to go ahead and source this, and the only line that isn't commented out is the one that tells GDB where to look for our library. So pretty simple. Now, if we try and break main, it says function main not defined. Function main not defined, you might ask, what does that mean? Well, when we did -s to strip our binary, what we actually did is we removed all of the symbols. So symbols are what we use to say, okay, this function is named this. So the function main is named main, right? Yeah, unfortunately, no. If we strip it, there's no reason that that function has to be named main except that it's helpful. And in reverse engineering, people don't want to be helpful. Companies who are giving you programs will strip their programs so that you don't know what things are called. That's called either security through obscurity, or B, just being a dick, so that you don't steal their stuff when they really should be releasing their things open source. But, you know, that's the world we live in. So we're going to deal with it. and we're going to figure out how to debug this program without being able to set breakpoints at particular functions. So what we're going to actually do is we're going to do something called start I. So what that does is it starts the program at the first instruction, and then it's going to stop. This is a very useful thing for debugging with no symbols. So start I. Now, where are we? We're in the loader. The first thing that is executed when we run a program isn't our program, it's the loader that's putting our shared libraries into place and things like that. But what we can do, now that we've loaded it, is we can break at init. Now, init is always going to be defined unless somebody did some serious magic. So this is a really good way to make sure that we have a breakpoint we can actually use. So now if we continue, we'll stop at this function. So if we go next, you'll see that we want to step into this call, not over it. And if we continue to step, we will get to, where are we at? Register TM clones. Okay, so you're going to see this a lot, and this is why I wanted to talk about it. You're going to see this function pretty much every time you reverse engineer something. Every time you see it, you're going to say, what is that? Is it important? Do I need to know what it does? The answer is no, you do not. So from here, basically, you didn't need to do all of that stepping. I just did it to prove the point that register TM clones is a very specific but super stupid thing that you need to know about, but you don't need to know about because it's useless for reverse engineering purposes, usually. So instead what we can do is we can break start. No, okay, we can't. We can break at libc start main. So libc start main is what's actually going to call our start function in our program. So again, this is part of the standard library, not part of our program. But if we continue to it, what? I might have made a mistake here. All right. I'm going to start over debugging this. So we're going to go start I, and then we're going to break init, and then we're going to break at libc start main. Okay, that's fine. And we forgot to source our thing. So now we're getting into I'm actually reverse engineering instead of I'm going through examples. So we're going to source gdb init. We're going to break at underscore init so that we can get our symbols populated, and we're going to run our program with R. Okay, so now if we do, so this is a good learning opportunity. If we do something called info function, we can list out all of the functions in our program, right? So this is everything that's loaded into memory right now. So you'll see a ton of stuff because the loader has put standard library into our process image. But if we do info file, now that we have done start I and we've set a breakpoint at underscore init, our entry point will actually be updated very helpfully by GDB with our relocation information of where we are in memory. So before, when we were running programs that were compiled with no pi, our entry point was always 400,000 something hex. Now, our main executable is also position independent, so it can be put into memory at any place. Which means that until we start running and the kernel and the loader put us somewhere, we don't know where that's going to be. So that's why even if we knew what the address of main was in our elf file, we wouldn't be able to set a breakpoint there until we start somewhere. So that is why start I is very helpful. So just to recap, I just ran info file, and then up at the top we have entry point equals this value. So now if we do break star, don't forget the star, at that address, and now we continue, and we had a breakpoint in it, so we're going to continue past that again. Now we are at the beginning of our function. And notice we no longer have it say main plus anything, because GDB has no idea that this function is called main because of the stripping that I talked about earlier. So this binary is stripped, we have no symbols, so we don't know that this is main. But if we go ahead and step through it, we'll see that, wait a minute, this doesn't look like main at all. This is actually our underscore start function. So how do we know it's start? We'll look at that when we get to Ghidra. But this argument right here, this first argument to start, is passed in RDI. That is our address of main. But we are in start, so we can go ahead and step into, and we're going to continue to step. Did I step past main already? Hold up. Okay. Now we're I think in our binary. Yeah, all right. So 100% my mistake. Basically, if your program is stripped, you're gonna have some issues because it's kind of a pain to tell where you are. So basically, the process that I follow is stop at init, print out what our actual entry point is, and then just step until I get to main because I know we're gonna get there soon. So if we go ahead and continue to step, we're going to basically be in our program now. So it's pretty ugly, right? We're seeing a bunch of crap, and yeah, this is debugging with no source and no symbols except for our library symbols. Now, how do we make this better? We can use Ghidra, right? So we don't always have to debug. We can also, let's flip it over. We can also statically reverse engineer things. So I'm just real quickly, we're running very long here. I'm just really quickly going to talk about the high level reverse engineering process, and then I'm going to talk through using Ghidra a little bit on an example of selection, which is if statements essentially, and then we're going to be done. So if you're getting tired, I am too. I'm very hungry, so we're going to get through this, and Friday will likely be significantly shorter. So anyway, reverse engineering, primary steps. First, figure out what we're dealing with. So we looked at the file command, we looked at the readelf command. A command that I didn't talk about is strings, so we can run that on this program, right? Strings, it's literally the command strings program. And that's just going to print out all of the ASCII strings in our program. Notice there's not many because we've stripped it. But even just that one string is enough to give me a little bit of information about what's happening, and I know that's probably going to get printed. So using information about the binary to determine kind of how it functions before you start diving into assembly and debugging and things like that is a really good idea and can save you a lot of time. Next, we want to survey the target, right? So if we can list how many functions it has, if we can see how big it is, all kinds of things like that will let us speed up our analysis of it. And we'll look at kind of some better examples of that when we open up Ghidra. Next thing, determine control flow, right? So if we look at our program and, oh, I skipped past identify key locations, right? So we just want to, as quickly as we can, figure out what functions seem likely to have what we want. For CTF, that's going to be what functions have things that look like they might decode a flag or encode a flag or check a flag, anything like that. For industry reverse engineering, you're more likely going to be looking for vulnerabilities. So we're going to talk about looking for vulnerabilities when we go through binary exploitation, but that's another key location, right? Then you want to determine control flow. So you want to figure out, how can I get to the function that does the thing that I want? Very nebulous question. Sometimes the answer is more than one way. Sometimes there's only one way. You might need a password to get there, etc. Then dive deep and rinse and repeat. So at some point, you're going to have to actually read the assembly code of the program you're running. Our goal really is to read as little as we can, because the more you look at it, the more complicated it seems, right? So just to put that in a little bit more practical terms, use the file command, use binwalk, use readelf, use strings. Then you want to get into disassembly or decompilation. We're not going to decompile anything today, but we'll talk about that on Friday. And then using things you've identified kind of as signposts, basically you just want to say, all right, this string looks like something that indicates this part reads a flag. So I'm going to go ahead and look at that. If there's no strings and nothing else, usually I just start reverse engineering from main and kind of labeling functions with what I think they do. And then, obviously, if it's a complicated program, you're going to want to look at structures. You're going to want to look at the file formats, any what kinds of transactional data operations it's doing throughout the program, things like that. And yep, rest of the fucking owl. Reverse engineer it until you get what you want. So, like I've been saying all along, the objectives in CTF are a little different from typical reverse engineering vulnerability research stuff. All right, so let's open up Ghidra. Basically, we're just going to type Ghidra into our terminal. And we're going to get a tip of the day. I'm going to say, no, don't show me tips. And then we're going to get this project manager. So probably you will have a window that says, here, I'm going to go ahead and delete this. Oh, okay. You may have a window that says new non-shared or shared project. Go ahead and click on non-shared. Shared is nice. It's a good Ghidra feature, but you don't really need it so much for CTF unless you want to work with other people in the same binary. So yeah, you'll probably see new project, go to non-shared, bootcamp, finish. And that's all you really need to do in this window of Ghidra. Really what we're interested in is clicking on this dragon. And make sure that everything fits on screen. All right, so to import a program into Ghidra, what we're going to do is File, Import File. And we want to import from Bootcamp 2020 Rev, Day 1, 07 Selection Challenge program. So you'll get import options. The default is fine for x86. Usually it'll recognize exactly what it is. And then you'll get two pop-ups, one that says program has not been analyzed. Would you like to analyze it now? Go ahead and click yes. And then again, the defaults are usually fine for x86. It's only with weird architectures that you might need to mess with them, or if somebody has done some nastiness. And then go ahead and click OK on this. So Ghidra is going to, it's already done for me, but Ghidra is going to go ahead and analyze this program. And you may have a decompilation window open here. So if you have you probably have decompiler open. I'm going to go ahead and X that out because I'm not going to talk about decompilation until Friday. But if you look right here, we have an elf header. So this is exactly what we were looking at earlier. It's just what readelf would have told us about the program. And then over here, we have all of the segments of the program, sections, because we're reading the elf header or the elf file on disk, not from memory. And then we have two very important things for Ghidra. One is the symbol tree. So if we open functions, somebody in chat says R2 plus cutter is better for some stuff. Absolutely true. It is not better for newbies unless you really like it, but go ahead and give it a try. So there's other reverse engineering platforms you can use. IDA has a free version that lets you reverse engineer 64-bit stuff. IDA's super good. The only problem with it really is that it's expensive and it's a little old, so it does some backwards stuff. Binary Ninja is not free. It's what I personally prefer, though. It has a really nice interface and it works super well, super fast. It's easily scriptable. Radari 2 is a command line reverse engineering tool, and Cutter is a command or a graphical interface for it. So that's really good if you want another free reverse engineering tool. And then there's some others, but those are kind of the main ones. All right, so over here in our symbol tree, we have imports. So we can see we import from libc6.so. That's shared object. We have exports, which is the functions that we're exporting. So you see we have check A, check B, main, and then the rest of this is inserted by the compiler. And then most importantly, we have functions. So under functions, we just have a list of every function that's called in this program. So we have cxa finalize, libc start main, we have finish, we have init, we have start, which I was trying to find in GDB earlier, and due to the difficulty that I was trying to prove a point about, couldn't. But you see we have a main here at RDI. And yeah, so if we go ahead and double click main, you'll see, so immunet, this binary is not stripped. So if we compiled this binary stripped, we wouldn't have main, but we would have Ghidra probably recognize start. It's pretty good at that. But after I do this, I can go ahead and recompile this script and we can look at it. But this is actually a different binary than we were looking at just a moment ago. We were just looking at 06. This is 07. So if we go ahead and go to main, we see basically what we saw when we disassembled it in GDB, except that, you know, things are clickable. We can go to fgets and we can go to this other function and stuff. So already it's a little bit easier than GDB. We also, on the left side, have these nice little control flow indicators. So this is a jump instruction, which means we jump somewhere else in code. And this little indicator is telling us where we jump, right? So we jump down to pop RBP return. Now, the most powerful, well, maybe not most powerful, but one of the more powerful and useful things about these reverse engineering tools is they let us do something called a disassembly graph. So if we go to Window and Function Graph, we'll get a graph of this function. And so now it's really easy to see what the control flow of this function looks like. So we have a start of the function. We see that we have two possible branches from here. So we can either move 0 into EAX and then unconditionally go down to here, which is a return. So this is probably a failure condition on whatever this check is. Notice it's called check A. So we're assuming this checks something. And if you want to try your hand, I'm going to start from main and I'm going to go through this, but you're welcome to try and solve this challenge. This is actually a challenge that takes a flag. You're welcome to try and solve this challenge before I can solve it on stream. And that'll be our last thing for tonight. So let's go back to main in our function browser. So if we hit this nice little back button, it'll take us back to whatever we were looking at before, but it, you know, can't take us, oh, it can take us to main. How nice of them. That's a new feature, actually. So we start at main, and now we can see the control flow through this function a lot more easily visually. So we have a call to printf, we have a call to fgets, and remember our order of arguments is RDI, RSI, and ESI is just the lower 32 bits of RSI. So just consider those the same for the time being. So right now we're getting, and I should talk about man pages too. So if we open up Xterm, we don't know what fgets does. So if we want to know, we can type man fgets. Oh, I don't have man on this. Well, that's an exercise for the viewer, is try man fgets and you'll see what the arguments are. Anyway, our first argument is RAX, which is standard, not standard in, that's RDX, which is our third argument. So our third argument is standard in. Our second argument is our base pointer plus -20, so really -20. So remember, in our stack, base pointer, go down 20. So that's probably some of our stack space, right? Then we have our second argument, ESI, OX12. That's the amount we're going to read. Our first argument is RAX, which we set equal to this location. So if we put that all together, we have, and if you hit semicolon in Ghidra, you'll type a comment, fgets, buffer. So we know that's probably OX20 in size because of RBP, and I don't see any other stuff that's allocated on the stack here. OX12, standard in, right? So we're getting OX12 bytes from standard in into a buffer on our stack. And I'm not going to save that because it was ugly. Then we move, so remember, we have this buffer at this location, right? RBP minus OX20. And we're going to put that into RDI, which is our first argument to a function. Then we call check A. So if we go ahead into check A, we know that we're calling it with an argument of our buffer. So what's the first thing we do? There's not a great way to make this window bigger, so I'm actually going to go back to our linear view. So the first thing we do in check A, so this is the same basic block that we were looking at right here. The first thing we do is we move RDI onto the stack in our check A function. So this RBP plus local 10, and we can look at what the value of local 10 is, but that's just stack minus OX10. So we're just moving that value into the check function. Then we're going to get a pointer to that in RAX, right? Then we're going to compare that first byte against OX66. So what is OX66? Let's go ahead and open a terminal and find out. I like to use Python for this. If you cast anything to a character in Python, it'll print it out as a character, so that's F. Looks a lot like the first character of a flag, huh? So then we can see that we are adding 1 to RAX. So remember, RAX is a pointer to the first byte of our flag. If we add 1, we're going to have a pointer to the second byte, right? So we're dereferencing that pointer and moving it to EAX. And then we're comparing it against OX6C. So if we look at this, OX6C, that's L. So this is definitely our flag, right? So if we continue on, we see 6C, 6.1, 6.7, 7B. So this is an open bracket. And now if we just if we go ahead, and it's a little hard in this because we've got these small little windows, but it should work. So I'm just going to write a quick little for loop in Python. I'm going to start OX70, OX6B. And notice that on each of these, we're comparing, right? And then if the result of the comparison is 0, i.e. the comparison was a success, because the compare operator essentially subtracts, and then you operate based on what the result of that is. So we're subtracting our current character from OX6B. If they're the same, the result of that subtraction will be 0. And so we can use jump 0 to go to this label, which is this. So if we succeed in the check, we go on to the next check. If we fail, we go to this label down here, which just returns from the function. All right. So if we continue doing that, we'll get, try and do this as fast as possible. 6.3, OX7.5, OX6.9, OX6.3. Oh, I haven't been typing. Then 6.8, OX30, OX30, OX7.3, OX7.5. It's a bit of a long flag. And then OX7D is going to be our close brace character. If we just do that, and then we print CHRI and run that, we get the inside of our flag. So a stupid bastardization of Pikachu, I choose you, as this is a selection problem. So if we go ahead and we go to our bootcamp directory, and then go to day 1, then go to 07. If we go ahead and run the program, we see, just like we saw, it prompts for a password. If we type in flag PKCUICH00SU close bracket, it's now going to say password correct. So we pass this check, right? And then you see we return, or we move -1. So remember I talked about 2's complement. I'm not going to go into specifics on how that works, but we move -1 into EAX, and then we continue to return, right? So this is going to go back to main. Okay, and I'm going to close the function graph, and I'm just going to go back to main, and then I'm going to reopen the function graph because I don't really use Ghidra for this much, and that's the best way I know how to do it. So call check A, it's going to move, we can see EAX, so that's the return value from A. So we know we passed the check, so we're returning -1 into this location, right? Then we do get C, which presumably is to clear a new line. And then we compare -1 to the value at RBP plus local 30, which is where we just stored our return value from check A. And if the return value is not 0, we jump here. And we can see that this block will printf error, right? So if we don't return -1 from that function, we will get an error. But we got the password correct, and so we did printf password correct pin. So there's obviously a second check. Now we already found the flag, but we're just going to go ahead and look at slightly more complex control flow in check B. So if we go ahead and go back to the code browser, or the function graph rather, it's a little uglier this time. So again, just to make sure everybody saw that, right before we do check B, we fgets another OX8 characters, right? So if we go into check B, open our function graph, basically we're going to assume it's going to check each character again, because I'm not talking about iteration, I'm only talking about selection. So if we look at this, we get a pointer again to our, right here, we're getting a pointer to our string, and then we're dereferencing the pointer into EAX. And first thing we're comparing against is OX2F. So what is OX2F? that's slash. So what's it doing here? Well, we're actually seeing if we're less than or equal to that. So if we do, and I don't know if it's going to be installed. Okay, it's not installed. But just as an exercise, if you look at either the output of the ASCII command after you install it, or you do man ASCII would also work typically. Either of those should print out the table of ASCII characters. And if we look at OX2F, we want to jump if less than that to the fail. We're basically just making sure we are greater than OX2F, right? So with this jump if less than or equal to command, instruction. Then we're going to, again, dereference our pointer to the current character in the string, compare against OX39. If we're greater, we're going to, again, jump to the fail. But if we are less than OX39, we're going to come over here. So I'm sure you can all see where this is going. We're just going to follow the control flow and figure out which paths fail, which paths succeed, and then go based on what we're comparing against. So an important thing to look for when you're reverse engineering a program is what values we're comparing our inputs against, at least for CTF stuff. So control flow with if statements is one of the, as I said at the beginning, 3 main parts of a program. We have iteration, selection, and can't remember the third one, but it just means that executing instructions in order will do things in order, basically. So moral of the story with selection, look at your comparisons, see what you're jumping if less than or equal to, and then you'll know that the answer to this is CTF. And then our password is leet666, enter, and it'll say logged in. So I'll leave that up to the watcher because we are very, very out of time. But basically, this is just a sequence of jump if greater than, jump if less than. And then it's up to you, the reverse engineer, to figure out what value will actually satisfy the conditions to let you move on to the next check. So this is a very common paradigm for simpler level CTF challenges in reverse engineering. We'll be checking inputs, and that's most of what my examples are going to be, but we're going to keep adding things to it until we get back to that example I did at the beginning, and solving that with scripting and reverse engineering and all of that stuff. All right. No, I don't want to save it. Thank you, Ghidra. All right. So it's been 3 hours pretty much on the dot. Bit of a long presentation. But I feel like we've pretty much covered all the basics of reverse engineering. If any of that wasn't clear, absolutely feel free to go back on YouTube, watch it again, run it back, and feel free to shoot me any questions on our Discord. I'm going to drop our Discord in chat. Well, actually, I'm just going to drop our website in chat, but if you just go to CTF.boilers.com, there's a link to our Discord, so please feel free to send me any and all questions on there, and I will answer them as best I can. Yeah, no problem, Norman. I'm absolutely happy to. It's been pretty fun putting this all together, so I'm glad that we could broadcast it to everybody and get people involved from theoretically around the world. So thanks for watching, everybody. 35 people still watching. That is incredible.
Seesaw's
Nate.
this weekend, so don't forget to play that.
Yeah, play Seesaw.
Not a member of Boilers.
Yeah, if you're not a member of Boilers and you want to play with us, just drop a message in our public channel. I think we'll probably be cool with just letting anybody play with us for Seesaw this year. Since we're doing this publicly, it would be kind of fun to play with some more people. And if you have questions about reverse engineering while we're playing Seesaw, I'm happy to guide you on stuff. Seesaw is really good because it's targeted at beginners. So theoretically, even just with the knowledge that we learned today, you should theoretically be able to solve at least one challenge at Seesaw. Probably more though, because they tend to have like several really easy challenges for not easy. I don't want to say easy. None of this is easy. It's very difficult stuff, and it takes a lot of practice and things like that. So if you don't get it, don't worry about it. It takes practice and it takes learning. So yeah, Seesaw this weekend. Thanks everybody. Hope you learned something.